Yeah. Is it
Yeah,
visible?
thank you. Thank you very much.
Yeah. Yeah. Is it okay?
Yes, yes, please. Yes,
Yeah.
please.
Yeah. Yeah. So, good morning. So before starting the talk, and I hope when I was looking to the participants and everybody is PhD, so maybe you are faculty in some department. It is also the faculty development program. So the motivation is that to just to rewind, or you can say that it is the a faculty relaxation time and gain some advancement or some basic idea, or the other how we exchange our ideas that others are doing. So that's what the FDP program it is started, and I thanks to the organizer and Professor Swai and the NIT Manipur to organize such beautiful programs, and the different faculty members and they come. And one thing I'll tell you that why I talk it, that when you go to the class, and first of all that students should attend to you that what you are going to speak. So that's what I'm just giving some introduction that what we should do when we enter into the class, and then we should make sure that the student is attend to you that you are teaching. And maybe some of the slides or some of the concept you may know already, and I will be happy at the end for the comment, and that what we should improve and how we have to look at it. So I've chosen the topic that optimization of physical properties in polymer nanocomposite. Looking at the your FDP program, I have taken this, and I'll tell you that means we are catering in the different direction of our research. However, I have chosen this for the today's talk because it is very easy and the relaxing. You can understand that exactly what I'm going to tell. And I'm not going to, as you know, that study is very limited. I'm not going to tell you anything, something very different or some idea we have developed. It is not, it is the routine job. So I'll just rewind. That means it is just that you will be getting that exactly what is happening in a solid state physics, and what it is happening and what you can do when you are in a place where you have limited facility and all, as an experimentalist, how you can explore the research idea and these things. So, so I'll go one by one before going to that. And this is my common slide. You may have seen that it is our department. That if you have not seen that, I want to show some photo. Nowadays, Google, you can get everything, but still, and I just want to give a thrill that this is our gate and the science building where we have set it our lab, and this is inside some glimpse. It is not all total, but some glimpse of our lab which we have developed in last 10, 15 years. And there are a lot more facilities, but what I am taking care, and that only I've taken, like XRD, SEM, and your P loop tracer and arc melting furnace, and so on. So there is we have TM, VSM, and those things we are taking care, and also the dielectric measurement. And this is our current research highlight. We are working in the different materials, like mostly magnetic materials, and where we, I mean, so many PhD has been come out from our group, and also some of the papers are highlighted in the journals, and also appreciation, and so many awards by the students, and like that. So that is also, we have some patents that we have done out of it. So however, I will not go details about it. That's what I told, that I have choose the topic that polymer composite, polymer composite. Before going to the talk, let me thanks to my PhD students and funding agencies, IIT Patna, and my collaborators, and national and international, as well as my postdoctoral students, MTech students, for giving me the opportunity to enhance my CV and do some science, because they are the workers. Basically, they prompted and they forced me that to do it. And once again, thanks to the NIT Manipur for giving me this opportunity to share our research outputs. And special thanks to the participant, and as you know that I told you, the student, if you don't ask me, and I don't nurture my brain or my idea. So that's why you are the participant. I am able to speak because you are here and you are trying to listen me. Fine. I hope you relaxed. I did not tell anything and comes back. And if anybody has a doubt or if anybody wants to contact me, and I've given my email, and you can definitely drop a mail, and I'll try my best to address. So now comes back to our original topic, that is the nano composite.
Madam.
Okay, please. Background noise is coming. Background noise is coming.
అవును
Background noise is coming.
మేడం వైబ్రేషన్ లో పెట్టుకున్నారు అవును నేను
Hello, Professor Swang.
నేను లాస్ట్ టైం కూడా చెప్పాను మేడం.
Hello.
I don't understand why they're joining with the lots of. I mean, if you're not interested, then why they should leave.
Okay.
So please continue.
Yeah. So before continuing, and let me tell that as we are teacher, and you know that means the background noise and all, and we are at in online. Agree, but the question is that time is very, very important. And remember, and, from here our talk starts. We are professors, we are the students, and we are the educated people, and we know that in the physics, and the great scientists, they have tried to incorporate a single parameter, that is the time, and we don't realize what it is importance in our formulation. I'm starting my talk, and that is the physics. That you know that when Einstein could not do it, they tried how to incorporate in our formulation. Einstein could not do it, and also Dirac could not do it. So they are the weak scientists. They could not do it, and again they use the gauge to put it. And what is that gauge? That gauge is in the reference to the position. So we till now we could not incorporate the time factor in our formulation. Whatever we are doing in the terms of the position. So why did I tell this philosophy of the physics that the time we are unable to incorporate in our equation? And I am opening this question. You can go and nurture as a faculty. You can find out that time we have not incorporated. We are writing, and if you look at it is a reference to the your city, ICT, whatever you are writing. Again, you are bringing the velocity. Independently, time is not in our formulation. We are unable to catch it because it is a parameter which nobody can predict or nobody can exactly incorporate in the physics formulation. Why did I tell this? And because we are gathered here and you respect your time and respect to the other's time. So that's what I told, that because time we are till now we have not formulated. The day we will formulate in physics, and I hope and we can we can do such things. Okay, fine. So this is a open problem, and you can go and look at the Dirac formulation or your Einstein formulation. You can find, and they also write that they are not able to incorporate time independently. It is respect to the position, so we can tell about our position, not the time. So that is the physics, some fundamental. I'll not go there, and today I'm going to talk about the polymer nanocomposite. So this polymer nanocomposite, and then I'll tell that what is the importance of this. Then I will say that the what are the factors affecting physical properties in the basically your particle size or the percentage. That only two questions will answer at the end. That when we are going for the nanocomposite, really the size and size of the nanoparticle and percentage of the nanoparticle, does it affect the polymer properties, and why we should do that? why we should do that, that I will give some example what we have explored and two examples, and I will tell you that what exactly it happens. We will understand exactly the composite. Again, the question, it is a nano composite, then we will also answer the third point, that nano composite, is it same as the composite and where you reduce the size and call it a nano composite? Is it true? That if it is less than 100 nanometer and some particle and I take it, then I'll tell it nanocomposite or not. These three questions. Once again, I tell, when you are going for the nanocomposite, and first of all, we'll see the definition of the composite, and by name itself, it is a combination of two or more materials. So it is a composite that we are combining. So when we are combining two materials, why call it is the nano composite? People also you will find in the textbook it is composite. What is the difference between them? So that we will answer. Then we will answer that when we are putting the material, one material into the other, when we are mixing, if you reduce the size below 100 nanometer, can I call these two materials they have combined and form a nanocomposite or not? That is the second question we'll answer. Then we'll see that that what size in the polymer one has to put. That answer will give. Then that question it is that how much you can put inside the polymer. By this question, and it may have, if somebody is working or if you have processed in your brain, you will understand that, okay, then size and the percentage, it is a matter. It is a matter. And how it is matter, that we are going to answer in this talk. Okay, so that will be your take home message that what you can do. Okay, before going to that, just I will brush up your knowledge that let us see that we have in the condensed matter physics, it is a very big. But if you look at the fundamental, and that's what I told the name to scientists, the Einstein and Dirac, if you go and their fundamental physics is very, very small. But they use the mathematical tools or or they hire the mathematical tools to show their assumption. So if you look at our assumption in solid state physics, we have assumed not only solid state physics, entire material world. We have explained, you will be surprised to know, only this electron. And we have assumed it has a charge, it has a mass, and it has a spin. We have formulated, we have assumed this, then we have explained all other particles, subatomic particle, atom, molecule, and like that. Initially, we were trying to tell by assuming there is an atom and it has mass and like that. Then we say that no, there is an electron beyond the atom. It has these properties, spin, charge, and mass. Then relative to the electron, we have defined our neutron, proton, then again quark and other things. And whatever you do the formulation, finally you have to return back that what the electron is doing. Similarly, your means your classical mechanics, I did not tell, very interesting there. Mechanics is very small. In the classical mechanics, whatever we do and we try to prove that Newton's law, that is the observable, and it is showing some results. Similarly, in the conventional material world, we have taken the electron, it has a spin, it has a charge, and it has a mass. Okay, so that we have and very interesting that the Dirac formulation of our spin, that what he said, and that's what I was telling about the time, and that if you are observing magnetic moment, if you are observing, this is the assumption, not that it is the some real experiment and something, that is the Dirac assumption. If you are measuring the magnetic moment of an electron, what you will get a value, constant value, but its direction will be different. Direction will be different if you collect all the magnetic moment with the direction from 0 to infinite time, 0 to infinite time, then plot it. That is the assumption. It is not that experimentally it is done. You plot it. What you will get? You will get a spherical, symmetric, basically all the top point of the magnetic moment, if you consider classically arrow mark, and they will be placed in a surface of a sphere with the radius that is nothing but your magnetic moment. That will be the magnitude. So now you see the radius, anywhere you put it, it will be plus half and minus half. We call it that the magnetic moment, the probability of finding it is either it will be in the plus half of the sphere or the minus half of the sphere, and that plus half and minus half, it is the, you can arbitrarily choose it. It is not that it is horizontal and like this you are cutting. It is not like that. Anywhere you can cut, it will be plus or minus. That is the formulation of the spin. Then charge, we have said that it is a negative charge that we have taken, and we have taken its value. Then it has a particular mass, and that value, 1.6 × 10⁻19, and it is 9.1 and 10⁻31 kg. So that is the spin, charge, and spin. We have taken one Bohr magnetron. That's all we have assumed. then the properties of the material, very simply we explain how they are distributed on the material. That's all. How they distributed on the material. So am I audible?
Yes.
Yeah.
No problem.
So that is the formulation we have done, that the spin, charge, and mass distribution function, if you know in the material, you will be able to predict its property. This is the fundamental. Then when you are experimentalist, if you understand this, it is sufficient for us. Then, and this electron inside the material, it can be free. Free means probability of finding the amplitude of electron will be uniform throughout the material. That is our formulation. That is the free electron. Again, probability of finding the amplitude of the electron is uniform throughout the material. Then we call it is the electron is free. It is not that electron and the outermost shell and etc. This is the semi-classical way or semi-quantum way we keep on talking. But if you talk about the exact quantum mechanical concept, they say that it is nothing but it is probabilistic term. So that what we say, that the free electron, that probability of finding of the amplitude of an electron is uniform throughout the material, then we call it is the free electron. And if it is not uniform, then we call it is the bound electron. Why we call? You get the maximum amplitude near to the lattice point, then we call it is the bound electron. We call it the bound electron. It is not that experimentally we have seen this or something like that. And there are the properties and of the your material. To explain those properties, we have assumed the electrons are in some of the categorized the material. Some of the materials, the electron distribution function is uniform, and some of them are like the Dirac comb, or you can say that it is a high at the lattice side, then it is a zero away from the lattice side. So then we call it is the bound. So either free or bound charge we do. And but in the polymer, as you know, that polymer is unlikely they give the free electron, otherwise always there will be the bound electron in case of the polymer. And some of the polymers are there due to the pi bond, and they will have the free electron, but will not go there. But I will talk about only the bound electron of the polymer. So that bound electron property, that currently the dielectric materials, that they give you the dielectrics. Okay, we have given the name that dielectric materials have the great, and they have the great opportunity in the modern devices. You know that these dielectric materials, and they can be utilized for the energy storage device and solid state refrigerators, sensor, and actuator. And this electron, only this electron, and they behave, that bound electron behave in such a way that, and you can have the different applications, as you know that we know. So now with this knowledge, that we are going to restrict the bound electron property, and that is nothing but your dielectric property. So that we will see that the nanocomposite, we will understand first the composite and then nanocomposite, then we'll go. Composite materials are made from two or more materials with significantly different physical or chemical properties that, when combined, produce a material with characteristics different from the individual components. just you think you have the two materials, then they are coming close to each other, then what it happens when they come too close to each other? I think my hello. There is some problem. Okay, fine. So when you combine these two materials, and very simple, it is a van der Waals force, and as you know that the van der Waals force, it is a derived force, but it is exactly electrostatic force. When they come to closer each other, and again, I'm using the word, it is the derived force. We have only four fundamental forces. Any force you talk, they will fall on that. So when they come to closer to each other, that the two materials, they will be interact by the van der Waals force, and due to that in the surface there will be disturbance, that is the composite, then they change the properties. So there are the four types of the composite. One is fibrous composite, laminated composite, particulate composite, then combination of some of the all of the above. Let us see that we'll understand what it is happening exactly, and you look into that. We have given particulate means 0.3, or laminate means 2.2, and your fiber or rod is the 1.3. And if you look at the first one, you look at that it is a particulate, and we have written the 0.3. Then the question is what we mean by the 0.3. Basically, these green balls are the zero dimensional. Again, the question is coming, that is the fundamental one, is to understand what do you mean by the zero dimensional. Zero dimensional means, please don't confuse, it is a simple the atomic model. That means when you reduce the size of the material, they come to a stage where they behave like an atom, that means the assumption of the atom, we can apply and explain their properties. They behave like an atom, not an atom, but like an atom. So that's what it is, the zero dimension. I'm not taking you to there, and it is another very interesting physics is there. So that is the zero dimension. Then the three dimension, it is just a material, whatever classical you are looking, that is the three-dimensional material. So you can say the zero-dimensional material or the quantum material, but three-dimensional, the classical material, and very interesting how you will distinguish it. At the end, definitely I'll tell you the fundamentals that how you'll distinguish, and let me finish the talk because that is again, it will take some time. So 0.3 type, that is the zero-dimensional, and your three-dimensional when you put, then we call it is the particular composite. When the 2.2, that means your material, you look into the second figure, that green one, it is a 2D material, as well as on the top it is also another 2D material, and so they are laminated each other. Then other one is 1.3, one is one dimensional. What we are calling it is the one dimensional. If you look at the z direction or in the vertical, it is its length can be more than your quantum regime, and and the diameter can be in the quantum regime. So now you look into that this material is the two types, and in the 2D material, the your xy, or it is your seat is a classical you are looking, but in the z direction, it is the quantum effect. So very interesting that we have formulated, that's what we call the 2D. Then here it is the classical in one direction, but the quantum in two direction, that we call it is the one dimensional material. So that is the, and three dimensional, it is the just a classical material. So when I talk about the classical and the quantum material, remember, boundaries, never you say that x tends to 0, we write. What do you mean by that? This is nothing but, that is nothing but the parameter, it is 10 to the power minus 6, 10 to the power minus 6, below 10 to the power minus 6, I did not tell any unit. Why? Because 10 to the power minus 6, and you put the fundamental any unit, either your 7 fundamental units, any unit, meter, you put the meter, or you put your ampere, you put your time, second, any fundamental unit. So below that we call it is the quantum regime, because below that it is beyond the visible range. What is the visible range or classical range? That means what we cannot observe and modify, that we call it is the our classical range. Beyond that, it is not that. Remember, repeatedly I'm telling, it is 10 to the power minus 6, and put the unit of your fundamental units. Then below that, whatever you write, those are in the quantum regime. Above that is classical regime, because above 10 to the power minus 6 we can observe and modify. That's what we have distinguished in the science. Formulation is not flaw, it is always the fixed point. Fixed. They logically they put it that this is the quantum and this is the classical. Any formulation they do like that. So the background noise is coming. Fine. So till now I did not tell. Some background noise is coming. Okay. Fine. Anyway, so the nanocomposite, it is the nanomaterial. I told you that when nanomaterial, definitely your dimension of the material should be very low. So that's what it is, either rod or it is thin film and all. And already I told this is the 0D, 2D, and your rod. I did not go details. If you have any doubt, I saw some message, and at the end we can discuss and I will clarify if you have any doubt. 0D and 1D and the 2D. So that 2D materials, when you put it inside the polymer, and what happens, and the question it is coming, and they will be formed the, it is not that nanocomposite. So that's what I told, that first of all, one is that the dimension should be in the quantum regime, or you can say the nano regime. Then the percentage is very important. That why we call it is the composite and the no composite, that we'll look at. Okay, but advantage of the nano size, it is that, as you know, that very simple, no difficulty when you go to quantum regime. That means in the nano size, it has the only two properties. Don't confuse, only two things. It is the surface area increases, plasmon is formed. I'll tell you that. Let me read out this, then I will tell you that what exactly it prompted that its properties very different. Then I'll tell you that whatever we have written, it is decreased permeability to gases, water and hydrocarbon, thermal stability, heat distortion, temperature, chemical resistance, surface appearance, electrical conductivity changes, magnetic property changes, optical clarity in comparison to conventionally filled polymer. All the properties it changes, right? You can go to the Google or textbook, so many things you will keep on reading, but the question is that what physics says. When you come to the nano size, and remember our formulation, the what is the formulation? Any solid, you look at any solid, its surface will be in plasmonic state. I repeat, if you look at any solid, its surface will be plasmonic state. Then after one or two layers, it will be gaseous state. Then after one or two layers, it will be liquid state, then solid. But classically, those layers are in the quantum regime. That's what we are unable to observe it. That's what always we get a question when we are in the school physics reading and all. When t tends to infinity, what will happen to the your solid? We say that it will disintegrate. You will not get anything. Why it happens? Because its surface is in plasma state. Why the plasma state? Very simple. Because the surface atom always face a very high force from the environment, because the two materials or the two atoms are different. So the force between the surface atom of the solid and the gas, it will be much different compared to the solid, not solid atom atomic interaction. That's what you get a surface, and never you think that surface tension will be only at the liquid, and you can have the surface tension in the any material. But the question is that, is it observable classically or not? So that so So that plasmonic effect, we call it the plasmonic effect. That is the first it is plasmon, then it comes to the gaseous, then liquid, then the solid. So that's what we get the in the surface of a solid. Now you look at that. If you reduce the size, very simple. Any solid surface will be this property. So that's what if you reduce the size, and the surface atoms will be more and this effect will be more, so that will be observable. That's what the drastically the physical property changes, because you know that plasma gas, I'm talking about plasma gas and the liquid, their property is different than your solid. So when you reduce it and your plasma gas and liquid amount is much more than your solid inside solid, so definitely they will have a different property than your solid one, because when it is the solid classical solid, and the solid is more compared to your surface, compared to your much more compared to your surface. That's what you get a solid property there. Observable again, I'm talking observable means its value is more than 10 to the minus 6 and the unit of your fundamental quantity. So that's what I'm talking. So they will be observable. But when you reduce it, what happened? The surface property are observable and compared to your bulk property. That's what when you reduce the size and these properties, whatever the property you look, they will be different. That's what when we call it the nanomaterials, and what we give a definition, you reduce the size below the 10 to the power minus 6. Below to the 10 to the minus 6, not only 10 to the minus 9, also below 10 to the minus 6, the point where they will have a drastical change of its property, then we call that is the nanomaterial. If there is no drastical change of the physical property, we cannot say nanomaterial, even 100 nanometer. We cannot say they are the nanomaterial. Property has to change. No doubt, they will be in the quantum regime. They will have the dimension below 10 to the minus 6, but they should have the property change and observable property change, then only we call it is the nanomaterial. So with this definition, any confusion you come and you put, and you can answer that what is happening with this information, you can tell what is happening in the nanomaterial. So in the nanocomposite, if you add the to the polymer and wait to what happens, and these are the main important impurity, cracks, toughness, and impact performance it affects. If you have a clean polymer and you are putting the nanomaterial, then what it will happen, and polymer will have a long chain, then nanomaterial will add the impurity, and also sometimes they crack. And this point very simple, but this prompted you that what size you will put so that you will not have the maximum crack, and what percentage you have to put so that you can the best property out of the composite. So that's what I told you that we'll answer this, and I'll give some examples. So if you go to the textbook, and this is just a brush up, that it is not very difficult, and it is if you go to a mixture or a composite and you say that it is the Vagad's law, you can say, or you can say that it is a means a volume fraction law, that you just take the properties of one material, then the percentage you have put it in your composite, and multiply it and find out that what will be the effective other property. This is about your stiffness, that E1 is equal to EF, and VF and EM PM. That is basically your volume fraction of the your matrix. Matrix means polymer. In this talk, we are talking about the polymer, but matrix can be a metal or a alloy, no problem. So filler is something, it is means your material. Okay, means your filler means your nanomaterial. You can say that matrix is your in this talk we are talking matrix is a polymer, and F is the filler is a nanomaterial. Volume fraction will be always 1, VF and VM is equal to 1. Then you take it and find out, you will find a straight line, and this is the theory. This is the theory, and this is the model, that fiber and your matrix. So in the model, that is the Baggot's law we call, or it is we call it is the volume fraction law. So similarly, if it is that in the composite, if it is not uniform or very not ideal, then we put it is the E2 is equal to in the different form, 1 by EF and PF, and then like that we do like our capacitor parallel and series. So similarly, you can put it in the matrix and fiber in different way. And if you look into that in the matrix, fiber they are in the series. You just look at it, matrix, fiber, series. So that's what the formula is: 1 by EF, 1 by EF BM, and 1 by EM BM BF. So like that we put it. So then you just rearrange it and you get it. And you just recall your series and parallel connection of resistor and capacitor. We do it depending upon the property. So I hope I could make you understand that what happens. So if it is a non-linear mixture, then we put the non-linear constant. Physicists are very, very interesting. They just put what? The non-linear constant. If you look into that NL and N0, then formula is same. Other formula is same, but the non-linear constant, we just put it in NL and N0. So that is nothing great about that. Means to understand it is very simple. But now you comes to the important parameter that you look at that, you are just putting the nanomaterial and it is a polymer that they are going and sitting it there. The question is that how close they should come, so that they can show you a different property. If you look in that, this is the correlation function that from the surface, what happen, any surface it comes to the surface phenomena, the property will be propagated in the two direction with exponential function. So if you look into that, if they merge, quantum mechanically, if they merge, what happens? You will get the maximum value kxx. X is the distance. Then when they start separating with the distance L, then you get the e to exponentially minus L by lambda. Everywhere, any phenomena you go in statistically, you will find that your phenomena is changing exponentially. Only what changes? Your kxx and your lambda, that is a constant. Depending upon your properties, it changes. It can be anything. It can be magnetic, it can be your dielectric, it can be your properties. And cos omega dot L, and if it is a directional dependent, your means parameter like spin, then it will be automatically, it will take that when at the center, what will be the angle. That's all. If it is not directional, then it is omega dot L, always it will be give you the 0, and so that's all, you will get the 1. That's all. Okay. And so that's what this is the fundamentals and the correlation function, which gives you the idea that when you take the nanocomposite and what it happens. Okay. So before coming to it, and I'll just come back just a minute. You just look at this figure. Okay, just look at this figure. You'll find that in the left side, whatever one is written, it is a polymer. Then 2, 3, 4, 5, 6, and then the fillers are, and the your eighth number at the bottom. Eighth number at the bottom, and this is nothing but, it is your you can say that what I say, that it is your filler. Okay, filler. So now what you are doing, that polymers are putting small amount here in the seventh. You are putting the very small amount. You can see small amount here and here, and you are putting, this is your filler, and then this is your matrix. So, and a small amount of the your polymer here, but small amount of your filler, nanoparticle, it is here. Okay, so represented it is like that. If you look at that, you see that the interaction of them, it is this area. Interaction is this area and this area. Listen carefully. If you keep on increase, what happen? You just look at the sixth one, and their interaction, they are interacting also. Not only they are interacting, but they are also interacting. That means the correlation function, okay, had started acting with the filler and filler. Remember? And the moment they start interacting each other, no more we can call it is the nanocomposite, because in the nanocomposite, what happened, this nanoparticle and their plasmonic effect on the surface, already I explained the plasmonic effect. Plasmonic effect on the surface should create a different property, so that the overall property will be changed. So if you come to this stage, what will happen? The property will be similar to the composite. Composite means, in the composite, what do we do? We have the two material we are compositing. Now you tell that, I cannot tell that in this, and I can tell it here, and in this I cannot tell that this is a single nanoparticle, this is single nanoparticle, because they are interacting. So they will be a act like a, when together they will act like a material. So that's where the percentage is very, very important. One should be careful. Then experimentally we have observed, and it is not that in the biosingle we are talking about the theory. Experimentally we have what we have observed. If you look at here, and I've drawn it, and in the nano size and up to the around 10%, you will find that the property is changing. Then again, this region we call it is the composite, and it can happen in other way around. So property may increase or decrease. Properties will increase and decrease. So that's what the first question we answer. No, sorry, third question we are asking, that the percentage. If your filler, even if it is in the nanometer, nano size, if it is more than 10%, don't call it is the nano composite, because they don't show the different property. They show like a volumetric, whatever the theory we understand, and with that we understand that composite, not the nano composite. So nano composite now we fix because of the flexibility. I told that they create the crack, but because of the flexibility of the polymer, and it extend little from 10% to 15%, 20%, like that, they can take the load. After that, they start crack. I was just talking that what is the disadvantage. If you put the filler in the polymer matrix, so what will happen? They will start creating the crack on your polymer chain. So that 15%, what I'm talking about, that will be your filler percentage in case of polymer, but in case of the metal, it is something around 2%, 3%, and you go to the metallurgical industry, you'll find that they put the 2% zirconium, 3% molybdenum, like that, to make the strength better. So the nano composite filler, again, this percentage will be the modulus of your matrix, young modulus of your matrix, and sometimes to the filler. So that will be depend upon that. So there are so many applications already. Composites are used, and I will not review it. And you understand in the biomedical and in the industry and everywhere. Okay, everywhere it has been gone. And what is the advantage? That advantage of ceramic polymer nanocomposite, that is the low filler loading, and with a small loading you can have a better property. They looks like this. I've taken from the book, and this is the figure. You can see that this is the nanoparticle and the polymer chain. Large surface area without sacrificing the density, flexibility, it enhances the physical and chemical properties. That is the advantage. Okay, but several issues need to be addressed. That is the physical distribution, optimization of nanofiller to matrix ratio under percolation threshold limit. I told you the percentage, that not that all polymer, okay, I go and put it the 10% will say that, okay, its property will be enhanced. No, it may happen that that particular polymer will have the 8%, other polymer will have 10%. It will depend upon the Young modulus and the chain bond strength. And these are the two parameters. And that is the shape and size of the nanofiller, that is important. Then fabrication process, that is the type of matrix and the filler, like a polymer. Sometimes you go for the hot pressing, sometimes is the copolymerization. It is the important. Already I told you that plasmonic effect and the surface plasmonic effect is the main cause to explain the property of the nano composite. Okay, so there are the different applications. Already I told you. Then means will be say that functional material, that you can have the energy generation and storage, sensor actuator, thermoelectric generator, solid state generator, refrigerator, optoelectronic devices. Okay, so the materials are characterized or categorized in different classes, like dielectric material. I told the bound electron. I'll be talking only the bound electron. So the dielectric, ferroelectric, piezoelectric, multiferroic, magnetic material, and so on. So the polymer nanocomposite can be extended in any extent. So just this is a glimpse that how it looks like the ferroelectric material, and you get a complete PE loop, so that we call it is the your ferroelectric material. Then it will have the non-volatile RAM application, dynamic capacitor, tunable microwave devices, then pyroelectric detector, sensor, and optical waveguides. So there are the different kinds of the ferroelectrics. One is the normal ferroelectric, where you get it is like this, and low remnant and this thing. Then you have the relaxer ferroelectric, that is the low remnant polarization. Dipole exists above transition temperature, shows diffuse phase transition and deviate from crucial, no structural phase transition across TM, presence of polar nanodomain, presence of polar microdomain, then shows sharp phase transition. No dipole exists above Curie temperature, large permanent polarization. You see, these are the observation. Don't confuse. These are the observation. But exactly what the physics formulation says, the normal ferroelectric means it is a, again, correlation function between the dipole and dipole are uniform. But when you go to the relaxer ferroelectric, it is not uniform. Very simple. Okay, physics is very, very simple. It is never it makes confusion. We do the confusion while we observe, but physics never does the confusion. Relaxer ferroelectric, simple. Again, the fundamental I take. If the dipoles are uniformly distributed, then I call it is the ferroelectric. If it is not in non-uniform, they are the different kind, that is the relaxer ferroelectric. Okay, they're not distributed uniformly. So now the types of the material, you can see the polarization and the different way, that is linear dielectric, ferroelectric, relaxer ferroelectric, and anti-ferroelectric. And this is another factor. This fourth one, you look, this is the anti-ferroelectric. You will get the P loop like this. Okay, fine. So I'll not go to the beyond this, and I hope I give you the idea of what is composite, nanocomposite, and your ferroelectric material. Then I will tell you that the PVDF and oxide nanocomposite, and I will give you the answer. The PVDF, it has a flexibility, easy processing, low weight, and it is shows a dipole. Okay, so there are the other polymers. I'll not go to that. PVDF, it has the different kind. You just look at that. We have drawn it. If you have a ceramic material, in case of the polymer, very simple. It has a dipole. You look into that, it has like this. So the polymer chain will be like this, but due to this plasmonic at the surface or the charge, they will be, these are the electron cloud is here. So they will be bring the positive charge in your polymer matrix. You see that they have brought it. So it is your, if you look into that, this is the beta phase, and this is your alpha phase. And basically this beta phase, listen carefully, this beta phase is responsible for the dielectric, because there is a, you look into that, you have positive and negative, and they form a dipole. Okay, here what happened, positive, positive, negative, negative. So they don't form they cancel each other, they don't form the dipole like that. So the maximum dielectric properties or the dipole ferroelectric properties contribution from the PVDF is by the beta phase, and of course the delta phase and other phases, but beta phase. So the polymer, why we are putting that, these are the models. If you have a alpha phase, then if you put a polymer, what will happen? Automatically this positive, they will be interact here, and the automatically beta phase will form. That is the advantage, that when you put a ceramic, by taking that in the ceramic material, and the aim was that pick up the cobalt ferrite, which is also a dielectric material, but it will, when you reduce its size, and it will be nanomaterial, and it will have a plasmonic effect. So that plasmonic effect, when you put it into in the PVDF, so they will be creating the beta phase in more in case of PVDF, and CFO automatically it is a dielectric material, so you will enhance the dielectric property, no doubt. So if you look at the, means when we look at the literature, people have tried a lot that to optimize, that is our talk, that optimize the properties. So what we did, and we found that there is a gap, that the people could find that, and already in the theoretically, that CFO, if you put the 10%, you get the maximum property, but it was not uniform. Somebody 10%, somebody 8%, somebody 12%, and somebody 15%, somewhere it is 5%. So we could look at the literature exactly what is happening. Then we found that there is a case that if you put the different size, the people 5% different size, 10% different size, 12% different size, the size is not matching, then it is like that, okay, might be the you be missing that the chain breaking or the crack in the polymer. So then we pick up the CFO, then we prepared in the different size, and these are the literature survey in the different, so that whatever I told, then 10% was the, we limit the 10% because which is a means very threshold value for a polymer and a ceramic composite. So we put the 10%, we take the 10%, then we change the size, then put it in the polymer matrix. Okay, polymer matrix. That was the means basically means aim that to find out. So that CFO we took, then what we did, we just did the different hour and means ball milling and getting the size. And the question definitely it will come that in the ball milling you will not get the uniform size, but average size, because when you go to the industrial application or anything, it is not that means always you will have the very uniform size, the property, because dielectric properties are not that much sensitive for the very uniform size. So in the ball mill, and what we observe that in the size has to be little roughly, if it is distributed, it is fine. It is not that exactly 20 nanometer and 25 nanometer it will change. So roughly you can have idea what nanometer is not creating the crack and giving you the best dielectric property. So by taking that particle, then we prepare the PBDF and the CFO nano composite, 10% only. Nano composite, not composite. Nano composite. Then, and by putting the DMF, and just it is a polymerization, as it is polymerization, nothing else, the as it is polymerization without hampering the properties of the your PBDF. So then we take that. If you look at this PBD of CFO, it was almost alpha and very less beta phase. But when you put the CFO, that we observe that beta phases increase. Okay, beta phases increase. Okay, even if you can find out the percentage of the crystallinity of a polymer from the XRD by comparing the intensity. Then this is the cobalt ferrite, and with the different size and different ball milling, we get a different size, average size. Then we take 120, 30, 20, 15, and 11. You'll find very interestingly, and also the TM, we found that more or less it is very uniform, not exactly non-uniform, even the even it is ball milling, because CFO is very, very stable with a very good young modulus. Even when we go to the your FESM image with this, and we found that means whatever the prediction, this they are forming what, and like a granular, I'm sorry, granular, and with that we assume that okay, fine, that nanoparticles are there, and the your polymer is making the granular shape. And also the AFM, we found that is there any means they are sitting outside, but also we found that the similar size of the grains of the PBDF and CFO. Then when we go to the dielectric constant, measurement of the dielectric constant, and we found that it is 10%, and these are the temperature variation of the dielectric constant, the PVDF and CFO, 20 nanometer, 20 nanometer. What it is happening, and if you, this is the dielectric constant, we could find the maximum for the PVDF and the 20%. Okay, 20%. So the question it is coming, why it is so? There are the 15, 11, and 10, and in the 30 and 21, that is the optimization. Why it has happened? What is the argument? Okay, so I'll come back there. What is the argument? Why the maximum value we get it for the 20%? And you look at that, you have a polymer matrix. You can go back, you will see that. You see that you had the PBDF polymer. Then if you look at the microstructure, and this granular are very nicely it is formed, but when you go percentage with the 10 and or 11 and 15, what it is happening, there are the two ways possibilities happening when you go more than 20. This 10 is the nanomaterial, nano size 10 nanometer. So what is happening due to their surface energy, they are combining and forming a bigger one and creating it problem. Or what they are doing, they are making the smaller granules. Means nano is here 10 nanometers, smaller granule. Because the polymer and they are interacting with the, what is there? Interacting with the your nanomaterial, and they're making the smaller size. Listen carefully, they're making the smaller size of the PVDF grain when you are the small size. So the polymer size is less, also its dielectric constant will decrease because there will be lots of porosity and this thing in between of the two granules. So that's what we observed, that it is that 20% gives you the best property. So what I'm trying to conclude, that means it is not that it is the CF 10%, 10% that it gives you the best property when you put the 20 nanometer size. So then you will say that if you go to the even means say 10, 15, 99% or 12% or 15% or 5%. So what it will happen, it may the agglomerate or it may create the smaller granular, so that the property is not and optimized. Repeatedly, if you do, then we found that the dielectric constant is optimized for the 20%. Okay, so the main polarization mechanism is electronic polarization. This is just a means idea, that nothing to do with this optimization. What I'm talking about, that when you see the dielectric, it is the electronic polarization, ionic polarization, oriental or dipolar polarization, interfacial polarization. Okay, so that's what there are the different. And if you look into that in the low frequency, that sometimes we do the mistake, that's what I want to point out. In the small frequency, the contribution from the electrode is maximum, so that one has to remove that. If you look at that, and the around 300 and hertz in this case, and what it is happening, that it is almost constant, the contribution. If you plot it z dash and z double dash, you'll find that so up to the 300, that you can identify your electrode contribution, and you can deduct it and find out the exact value of the dielectric. So that if you plot it and you look into that filler size with the dielectric constant, and you'll find that 20% it is the maximum and others are less. And already I told you that why it is happening. So that is one of the optimization, that the size, if you change the size, then it will be different. And with the filler size, but you look into that your beta phase. Why did I say that when it is a smaller size, you have the smaller granular is forming and it is creating problem? Because you look at that your beta phase is not decreasing. Beta phase is increasing, okay, with the size. But what it is happening, they are creating the cracks. Beta phase is increasing in the 30, 120. So, sorry, but they're creating the cracks, which also we observed from the FM and your FECM. Then we found that exactly they're creating the cracks, so that on the dielectric constant it is a decrease. So the optimization is 20 nano. This is the model that what I was talking about. If it is smaller size, there is the possibility they agglomerate because of the very small size. And if it is bigger, the possibility is the crack. But you need to have a synchronized size to get a good material. So this is all about the PVDF and the size. Then this another, I'll tell you that we take the different composition with the different young modulus and the dielectric constant, and try to optimize again what it is happening. But we could find out, you look into that, I told that this is the nano region and this is your composite. Okay, they are the different. You look into that in the initially theory we were talking. When you put it and your beta phase is in the nano, it is different. When it is composite, it goes in a different way. In this particular case, the composite can give you the better beta phase and the property. But it is not at the 50, but it is the 30 percentage, and it can show. So that I told you that when you say the percentage of the filler and your percentage of the filler and the property, and I told you that it will be like this. If it is some dielectric, it is showing like that, or it may happen that it will be like this and the some small like this. And so this region is composite, and this region is your nano composite. That is the definition we change it. Okay, so this is the means another demonstration that how with the your PBDF and the another means your cobalt ferrite based, that chromium doped cobalt ferrite, how they are showing the demonstrating the nano composite and the composite. So then the BHF and PBDF, and here and we did the extensive work, and we showed that flexibility nature of PVDF. The PVDF, you can see that the flexible of the electronics device, electronic device for the use of the electronic device, and it can be hold its flexibility till the 30%, and then we calculate the beta phase and alpha phase from the XRD. You can calculate it. Then we see that the granular how it is forming, and these are the models that how they are coming and attaching to the ceramic means nano particle. And this is the demonstration when you put it in the means a larger percentage, and what happens. This is a smaller percentage and you get the effect. Then when you keep on going, the larger percentage, and there will be agglomeration. So the property, the cracks and all these properties, it will come. So we get that, and you look into that. I told you that in the depending upon the composition, it can be extended from 10 to little more. So we get the maximum value, that is the your means X content and the intensity ratio, from where we could find out the fractional beta phase. Then it is the dielectric constant. You see that when beta phase is more and your dielectric constant is large, then the polarization from the PE loop, we found it is also the more, it is around 25%. So it is what we want to say, that it is not that your filler percentage will be fixed for all the ceramic. It depends upon the Young modulus and the your properties of the material. And this is another way to find out the energy density of this material. And we just calculated, and I'm not going details. If anybody interested, and definitely I can means talk. And another information I want to give, while you are doing the dielectric, and the leakage current is very, very important, very, very important. It should be very less. Again, we found that the leakage current, and if you look at that, and in this figure, leakage current, you look into that, not only the dielectric constant it is happening, but the leakage current is not following that exactly what we are putting, because of the plasmonic exchange of the electron. Okay, but by optimizing all these things, and you can take that around to 0.25, this blue color. So 0.15 is the best. Although dielectric is a little less, but I will be happy to choose this material for the technological application, because its leakage current will be less. Okay, so another is that 2BNT and PBDF. And here also, if you look into the properties, and in the similar way with the different volume percentage, then we found that if you look at that 15%, and it gives you the maximum dielectric constant, that also it is optimized for the not only the ferrite, but for the and another BNT. So what is the take home message? Composite and nano composite are different from each other. That only we ask the question, that will answer. Then properties of a material can be tuned for application by making composite or nano composite. The filler size in polymer nanocomposite should be less than 30 nanometer for tuning the property. Filler size should be spherical or elliptical, that we, so that means we have demonstrated that if you have different size, they will not form the your granular polymers. The dielectric constant, energy storage capacity of PVDF can be tuned by using ferrites, filler. Electrode contribution to the dielectric comes at a low frequency. One has to be reduce it and remove it. And beta phase of PVDF can be increased by ferrite nanofiller, which enhances the dielectric and storage density. This is the message I would like to give. I hope I have completed within the time. And as I discussed with Dr. Swain, and many thanks for giving me the opportunity and pass the message. If any question is there, and definitely I'll be happy to answer.
Thank you very much, Professor Kaur, for a very informative, lots of information regarding the polymer nanocomposite. This is now open for a question session. If any participant has two questions, they can ask
Hello,
us.
sir.
Yeah,
Hello.
please.
Yes,
Please.
sir. Thank you for a very nice talk, sir. I want to just I have one query that you discussed about the nano structures uh, in view of dimensionality like 1D, 2D, and zero dimension. So, sir, in classical regime, if some material have a dimension in classical regime, two dimension in classical regime, then we call it two-dimensional material in view of classical regime. But in case of nano, if material have two dimension in nano range and one in classical range, so we call it two-dimensional material in nano regime. Am I right?
Okay, fine.
Sir, so in that case, if a material have a all three dimension in nano regime, we call it zero dimension nanomaterial or it's three dimension nanomaterial.
Okay. So you are talking about that if your dimension is less than 10 to the power minus 6 in all the directions, right?
Yes, sir. Yes, sir.
Then we call it is nothing but it is a nanomaterial. Okay. Basically, if you we do the some formulation in that way, but if you look at the exact formulation, it is the micro world. It is
Yes.
the micro world. In the
Yes.
micro world, basically, it is the when I think somebody wrote it is the quantum confinement. It is a different concept. We just bring it here, and it is a different concept. Believe me. And you see that you are also confined. You are also the confined, but you are observable. So that's what
Yes,
we
sir.
call it is the classical particle. What is the observable? Already I told the dimension is that
Mm.
conventional engineering or visible range or observable, not only observable, observable and modification by the human being. That we call it is the our classical range. Very interesting formulation. Classical
Yes.
range. It varies from 10 to the minus 6 to 10 to the power 3. 10 to the
Yes,
minus
sir.
6 to 10 to the power 3. That is our basically you can say the classical regime or conventional engineering also we use, or we
Yes, sir.
call it is our classical, and they are also confinement. I am also a confinement, classical confinement body. You are also a confinement body, but we are observable. That's what we call it is the classical confinement. When it is not observable, again, repeatedly I'm telling, don't
Yes, sir.
confuse. Observable means what the human being can observe
Observe.
and
Yes.
modify. So that if it is in that, if it is beyond that region, below that regime, we call it is the quantum regime, and then the quantum confinement, all these properties, all these theories are applied. Could I
Yes, sir.
explain? Could I
Yes,
explain?
sir. My little bit confusion is that if we have you told that if we have all three dimension in nano regime, we just call it in we are in micro world and we just call it a nanomaterial, right?
Yeah.
So and with that
No.
also
We
we
don't.
should
We
have one
don't call.
property that property should be
Yeah.
little different from the bulk one,
Yeah.
right?
Yeah. Yeah. Yeah.
Yes, sir.
Yeah.
So, but I want to know the clear-cut explanation about the zero-dimension material. Is that if we have all three dimension in nano regime with that quantum confinement, then we call it a zero-dimensional material?
Definitely. Your understanding, your explanation is correct. It is okay. Just a minute. Just a minute. We call it is the x tends to 0. Okay. Never we
Yes, sir.
think about what is the d del delta. Okay, so they
Okay.
are defined depending upon the dimension. Dimensionally, if you look at it, delta is the smaller than del and the smaller than d. Okay, so
Yes,
this delta, what we call it is the zero dimension. That I told you that this atom, okay, so
yes, sir.
this material we have like an atom. We can consider this is an atom. Whatever the atomic properties we are looking, if they show that material shows the same property,
Same.
like
Yeah.
your
Okay.
transition spectra, then we call it is the zero-dimensional material. Okay,
Okay.
if that material, you always I will tell you that, and whenever you read anything, please you see that what is the observation we are formulating. It is not that we have formulated and we are doing the observation. Observation is
Okay.
that they show the atomic spectra, like spectra they show. Okay,
Okay, sir.
so that I
Okay.
cannot call it is a material. I will call it is a just a quantum. It is like an atom, like an atom. There is
Yeah.
no identity. Basically, what we are assuming, there is no identity of the atoms. All atom has merged and they have formed.
Yes,
Basically,
sir.
means what I will say that what we have thought. Suppose in your house some thief is entering. So what will happen? And no more you people can be in one room or relax. All will be in the single mind and just to protect it. Are you getting my
Yes, sir.
point? So they, you
Yeah.
cannot think anything else. Similarly, you think that all the atoms will have a very high tension. That's what they combine each other and form like an atom. They behave like an atom. So there will be no identity of the single atoms inside it, and they all together will be behave like an atom.
Yes.
Could I explain? Could I
Yes,
explain?
sir. Yes, sir. Thank you. Thank you very much, sir.
हाँ हाँ मैंने बोल दिया सर का पहले होगा बोलो
हाँ अभी आप बाहर चलो
तो बैठी हो
Good morning,
Any
sir.
other questions?
हाँ
Sir, one question.
Yeah, please.
उठवा के माने आप
Is it a condition that we should not increase the filler material more than 10% in annual composition?
Okay.
आप बैठाओगे क्या
Okay.
पहले खिलाऊंगी क्या
Hello.
Is there any condition that we should not increase the filler material
Huh?
percentage?
So
Should
pillar
not increase the
material
filler material
should
more
be
than
around
10%.
10%. If it is a polymer, it should be around
That's good.
10% because before beyond that percentage, there may be the crack and you may not get the desired property. That's what it should be around 10%. Because I told you that if you increase the percentage, what will happen? The one nanomaterial will be correlate with other nanomaterial, rather giving the 100% correlation to the matrix. That already I told you. The correlation length, if they come closer to each other, between their correlation length, and they will not give you the best property. That's what it will be around 10%.
It is better to keep 10%.
Yeah, 10% plus or minus.
Yes, sir. Okay, thank you. Okay, thank you, sir. Thanks.
तो देख लिया मैं कह रही ठीक है
Any other questions?
hello
Yes, please.
I will request Dr. Kar sir if you can during mixing of two different sort of nanoparticles while making composites
Hello.
Yes, please.
I did not get the question.
Please ask the questions once again. Dr. Dhananjay, something. Oh, okay. So anyway, I think there is no more questions. So I thank once again thank to Professor Kar for his informative talk, and thank you very much for accepting my invitation and giving this talk. Thank you very much.
Thank you. Thank you. Thank you. Have a nice day. I hope all of you will enjoy the day.
Yeah.
Thank you very much.
Same to you. Same to you.
Thank you.
Thank
Bye-bye.
you. Thank you very much.
Bye.
Bye. So the next session is 12:15 by Dr. Jasnendu Giri, and this is talk is all about the biomedical engineering. This talk is the nanotechnology based antimicrobial surface, and it is very good. It is very informative talk. So I request everyone should join in the 12:15. So please join around 12:10. Okay. So 5 minutes before, then that is okay. So this is now time to take rest.
वगैरह मैं कर दूँ अब दोनों का ही है कॉमन है मैम कॉमन आप लोग तो बैठते पर आप लोग सभी को बैठे थे तुम लोग भी करते हो अरे और
जिस पे लिखना है का रजिस्टर नहीं सर अभी एक
फॉर्म ये है रजिस्ट्रेशन फॉर्म है रजिस्ट्रेशन मुझे
पेन ऑन नहीं है ये ना
इसमें एंट्री करा दो बच्चों से इसमें एंट्री करा दो
Okay. Okay. डोनेट करा रहे थे एथलेटिक्स क्या खेलूंगी मैं पहले दौड़ कर लेते हैं मैं तो कह रही पहले दौड़ कर लो बाद में तो ब्लड डोनेट कर अब इसके बाद सेकंड सर का हो गया ना नहीं हाँ एक बैग हाँ मुझे रखा बच के रखा है क्यों कर रहे हो कितना ऊपर यहाँ पे
ये तुम लगा सकते हो अगर ये बैंडेज लगवाना
नहीं नहीं कुछ रिफ्रेशमेंट तो दौड़ना भी था ऐसा कुछ खाया ऐसा कुछ खाया वही आपको बोला था तो मुझे चेक कर सकते हो कल हम देख लेंगे मैं अपने लिए कर देती हूँ खाली प्रॉब्लम केला तो बिल्कुल मत देना
बैठो नहीं आ गई घंटे कैसा लग रहा
थोड़ी मिलती थी बाकी
है
मैं रनिंग नहीं कर रहा हूँ,
रनिंग
तो नहीं करना है।
फिर भी रनिंग नहीं करनी। तो यहाँ पे ये भी लड़ाई थी फर्स्ट सेकंड और मुझे तो मैंने अपने बेड में दिया कुछ बेड यही दूंगी मैं से कुछ भी रजिस्ट्रेशन का तो आप ऐसे करें जब आपने नाम पहले ही लिख लिया तो रजिस्ट्रेशन का मतलब क्या लगेगा? जब नाम लिखा था तो पूछा था नहीं, जब नाम लिखा था तो पूछा था कि दोगे या नहीं दोगे फिर कुछ भी
फर्स्ट फीमेल
ऐसा कुछ कोई जरूरत नहीं
फर्स्ट
है,
मेल होगा
ऐसा कुछ लिखने की जरूरत नहीं।
मैडम का फोन ले दिया।
खुद दिया इन्होंने, मैं तो हटा रही थी ना बेड से, इन्होंने कहा मैं तो बैठी ही रहूंगी,
हाँ
हिलूंगी नहीं मैं।
हाँ नहीं, मुझे उसी बेड पे दे बेड नहीं छोड़ रही थी, बाकी सब कुछ छोड़ने को तैयार थी।
डस्टबिन रखाओ।
सारे मत खोलो, एक पैकेट खोलो राकेश, तुम लोग अपना ब्लड ग्रुप चेक करवा लेना जब आप करोगे। हाँ हाँ जब करोगे।
This is the meeting for nanotechnology seminar.
मुझे कुछ नहीं आता, तो बोला आधे घंटे बाद नहीं भाई, फर्स्ट डोनर नहीं हो, फर्स्ट डोनर वो फर्क क्या पड़ता है? तो मेरा तो कहता है मैडम आपको कुछ चेक करने की जरूरत नहीं है।
आपने ये रिबन कर लीजिए इकडे घेऊन येते का मॅडम एक और फ्रूटी पी
कुछ नहीं हुआ है,
भैया हमारे
आपने फूल नहीं दिया,
पैर खून से क्या मतलब, इनका तो ले गए वो, इनका तो ले गए। तो मैं क्या बोल रही थी वो, आप उनको राजेश पांडे जी,
क्या बोल,
मैं कहीं फोन लगा के आ रही हूँ, छाते पे हैं।
कहना लोग करने देते हैं कि सब कुछ करने, सब में ध्यान बैठे मार्गदर्शन दे, वो भी करने तो ठीक है।
अच्छा, मेरे को पता नहीं था आप कहाँ गए जब मैं रजिस्ट्रेशन फॉर्म भर रही थी ना, तो मुझे आप दिखे नहीं। मैम कहाँ गए आप?
कर ली
नहीं सर, ऐसा नहीं होगा, कुछ ना बोले, ऐसे ऐसे परेशान हो आपको बोलो, अगर आप नहीं बोलोगे तो फिर हम लोग फंस जाएंगे। वो आपको मना किया गया है, आप अगर बताओगे नहीं अपनी प्रॉब्लम तो कैसे चलेगा? बात वो है नहीं, बात बात अगर आप समझ नहीं है तो अपने फैकल्टी पे इतना लोड भी नहीं डाल सकते। आपको टेंशन लेने को बोल ही नहीं रही, तो करेगा कौन? हम आपकी बात को मान रहे हैं, तो आप कहो तो नहीं, इतना कह दो, इतना कह दो कि हमारी सारी फैकल्टी को बुला, इतना तो कह सकते हो, इतना कह दो तो हम सारे अपने अपना बोलना शुरू कर देंगे। नहीं बोल तब बोलेंगे ना, थोड़ी होता है कि 8:30 तक हम पागल बना के रखते हैं। तो हम बोलेंगे आप लोग काम कर सकते हैं, जो क्वेश्चन करें तो आप दे सकते हो। आप एक काम करना, हमारी फैकल्टीज को बुला लो, बस बात। पढ़ाना अभी अभी दिसंबर में सिलेबस बना के दिया, फिर सिलेबस बना के दो, पागल हो क्या? दिसंबर में स्टार्ट करना था ना, उससे पहले बना के दिया कि नहीं दिया? अक्टूबर नवंबर में दिया है, अभी बना के दिया मैम, अभी चेंज कैसे समझ? हाँ, बात नहीं है, लेकिन दो हमारा भी आप जहाँ बोलो नहीं होता है। हम क्या हर 2 महीने में सिलेबस बनाते हैं? हम हर 2 महीने में सिलेबस बनाते हैं नहीं, तो फिर आप एक यूनिवर्सिटी चला, स्टूडेंट कोऑर्डिनेटर काम करेगा, वो जो कह रहे हैं वो कर। हमारी मुझे काम नहीं देना है, लेकिन हम हर 2 महीने में सिलेबस नहीं बनाते। अभी नवंबर में बना के दिया था, तो ये हर 2 महीने में सिलेबस ही बनाते रहेंगे? तो हर 2 हम अभी नवंबर में दिया है, इस चीज के लिए तो बोल रहा है, नहीं बोलते ना सर, हर 2 महीने में थोड़ी लोग। मैं सर को, हम सब बोलने को तैयार है, हम तो बोलना तो बोलो, सबको सारी फैकल्टीज को बुला लो आप। मेरी भी हो चुकी है, अभी नहीं जैसे सर ने बोला आपने पढ़ाया कुछ, तो कहते मैं तो बायोटेक का हूँ ही नहीं, जब बायोटेक के हो नहीं तो फिर हमारा जो मामला करते क्यों खड़े रहते हो सर? सबके लिए सबको ये तो बोल रहे हैं, ऐसे नहीं होगा तो जाए। अब तो मैं तो कह रही हूँ सर, मैं तो सर को बोल रही हूँ सबको बुलाओ। कितनी बार सबको सब पे सब करके करो। मैं तो कह रही हूँ आपसे भी कुछ कहना सारी फैकल्टी मिलना चाहती है, उसमें पक्का मिलना चाहती है। 5 पीरियड आप पढ़ा दो, 5 पीरियड आप पढ़ा दो आके। तो फिर आपने टीचिंग मैम नवंबर में समझ दी है टीचिंग नाम बच्चा बच्चे का लिख के दे SOHIT से
ये अपना है क्या? अरे वो हाँ ये नील है ना, वही ठीक है ना,
तो नीली पेन से है ना ये।
तो नाम थी।
छोटा सा कोई काम होना है तो वो होना है, उसमें 4 घंटे वहाँ बैठे।
क्या नाम है? रोहित कुमार।
पेशर आपको सर्टिफिकेट लिख दिया।
ये कहाँ? ये तरुण कुमार है ना? तरुण ठीक है ना?
हो गया 7 मिनट रहो, लेकिन
जिसका चाहिए मेरे को तो
ना देखो करो बात है कौन है तो फिर आगे भी उसको करते हैं, हर 3 दिन के बाद सर वो नहीं
चलो मैम।
बोलने ना बोला, अगर वो खुदे ले तो वो सर हम इसको करता है सब लोग करता
अच्छा, अभिषेक सर ने अपनी फोटो डाल दी ग्रुप में।
दूसरा है
अच्छा, उन्होंने आके वीसी की फोटो देखी, मेरी तरफ देखा, उधर होके चले गए और उधर अभी अशोक सर की खींच कर अपनी डाल दी। सबसे अच्छे लोग तो यहाँ पे ये है।
इधर वाले
हाँ, मेरे को कुछ हुआ ही नहीं था।
थैंक्स टू टाइगर ने
कॉफी पी सकते हैं, चाय पी सकते हैं, बस आधा घंटा, थोड़ा आधे घंटे में पी लो। हाँ, बस आपने खाया पिया ना।
सारी बैटरी खराब कर दी।
ठीक है ठीक है एक लिया था फ्रेश कर दे मिल गया आपका फीड आप भरोगे
अरे तो सवाल पे निकालेंगे ना।
हाँ हाँ नहीं अरे पी लिया भाई उधर वाले पे लिया बाहर पी लिया मैम स्नैक फिर तक भरोगे तो नहीं तुम भरोगे हाँ मैं सस्ता दिया सच में पी के बैठ के उठी भरोगे तुम ही तो मैं भरती क्या लिखना क्या है कैसा लगा ग्रेट एक्सपीरियंस का और ब्लड देख कैसा ग्रेट एक्सपीरियंस और क्या लिखूं और क्या लिख दूं मैम परीक्षण कैसे किए तो मैंने की थी एक्सपीरियंस लाइफ टाइम मेमोरी ठीक है ये है और कुछ सेव लाइफ कुछ रखे ना एक अच्छा गुड इनिशिएटिव और giving something determinant of Thank you, ma'am. कोई चिढ़ा हुआ है बीसी चिढ़ गया था नहीं देख नहीं रहा तो उसका मतलब चिढ़ गया हाँ ये तो भाव दे देता है वो ये तो भाव दे देता है वो नहीं देता है तो नहीं दे देगी कुछ नहीं बोलेंगे वहाँ जाके ना गूंगे बन जाएंगे अपनी प्रॉब्लम भी नहीं बताते प्रॉब्लम तो उनकी ये है कि वो किसी के बुरे भी नहीं बनना चाहते और अच्छे भी नहीं बनना चाहते आप उनसे फीडबैक नहीं बनवाया आपने पीछे से हेलो मनीष सर सेल्फी लेनी है आपको अच्छा वो मनीष सर के पास चले वहीं पे बिस्किट भी मिल गया
ये बहुत चलो मैम बाहर चले जाते ओ मैम चलते हैं जाके चलते हैं। मिलना चाहिए संदीप सर को, अपनी प्रॉब्लम बतानी भी तो चाहिए। वो पता नहीं कौन सी डिप्लोमेसी खेलते हुए नहीं समझ में नहीं आता। वो खुद भी गए सर के साथ छुट्टी कर तुम क्या बोला है ठीक है। नहीं नहीं ऐसा कुछ नहीं है। कल की हो गई छुट्टी, कल हो गई छुट्टी। कौन कॉल करते हैं किसका कौन करते हैं सर इसी बात पहले पता है। अरे कॉल करते हैं जैसे जो आप लोग सुनिए ना तो अगले दिन की छुट्टी हो गई। साथ में घर में जाके काम करो तो आप फिर काम करो बस थोड़ी जो है भी बाकी कोई दिक्कत सारा हिस्सा है बाकी दो बोतल ध्यान दे। नमस्ते मैम, हमारे हिस्से में 2 बोतल आया है खून है मैम नहीं कैसे चलेंगे धूप में चलेंगे अभी नहीं हाँ तो नीचे ही होना है। चल रही नहीं दे खुद की चलानी भी नहीं है और खुद की चलानी भी नहीं है सबको ना करके असर करे और फिर उनके सामने जाके जी के लोग तभी इधर उधर ठीक कह रहे के सामने जिसने जिस तरह से देख के आया हूँ नहीं देखो लेकिन अपनी बात में तो 10 अंक वाले मोबाइल नंबर से आपके बैठेंगे बैठना कोई दिक्कत नहीं है बस उसको करना कोई ओटीपी साथ तो होगी मेरे कमरे में कैसे बोलते तो बात में कैसे बोल रही हूँ बैठ जाओ मैम बैठ जाओ अच्छा
डॉक्टर मनोहर चस्कर हा गुड मॉर्निंग सर मी धनंजय वाघोलीकर बोलतोय 1-2 मिनिटं बोलता येईल ना हा सर मला भेटायचं होतं पीएचडीच्या रजिस्ट्रेशनच्या संदर्भामध्ये थोडीशी बॅकग्राऊंड देतो मी सीओपी मधनं 1915ला 2015ला मी हा आज उद्या तुम्ही आहात का तिथे ऑफिसमध्ये तर माझं थोडंसं रजिस्ट्रेशन लांबलेलं आहे पण मला पीएचडी करायचं होतं काही गाईड रिलेटेड डिफिकल्टी आणि पर्सनल डिफिकल्टीमुळे राहून गेलं हा आज उद्या पण असाल का तुम्ही सर
यहाँ से देख लो कोई दवा कह के लिया कि भैया लेटरिन ला। हम किससे कहूँ? हो गया, फिक्स लगा दे थोड़ा बहुत। वो भी देखो क्या कह रहे, वो भी देखो क्या कह रहे। क्या कर रहा है तू? थोड़ा सा काम कर देगा। अरे पूर्णिमा के यहाँ चला जाएगा। यहाँ से यूँ कहिए भैया बच्चे को लेटरिन लग रही, 6 महीने का बच्चा, फोन नहीं उठा रहा भैया, बुलाते। ठीक है, यहाँ से कुछ करके दिया। कैसे कैसे देंगे?
टाइम क्या हो रहा है? एक भी नहीं।
जा रहा है दवाई। क्या? हाँ मैं जा रहा है पूर्णिमा वाले के यहाँ। मैं जा वहीं चल जाएगा दवा। हाँ ठीक है ना। हम कह रही है 6 महीने का बच्चा लेटरिन लग रही है तो
किसने बुलाया था? किसने बुलाया? किसने बुलाया? तुमको ऑप्शन दीजिए। आंटी को दे देना, इसके 2 हैं। आप तो खाओगे नहीं। मुझको आंसर ने बुलाया, फोन करने का था, आंसर आपसे मिलना चाहता है। मैं कुछ बोलूंगा ही नहीं। मैं कुछ बोलूंगा ही नहीं। हाँ देखो, अपने डिपार्टमेंट की परेशानी। बस नहीं, बच्चों से दुश्मनी नहीं डाल सकते, बाकी और कुछ नहीं कर। स्क्रीन भी सुनने में आ जाता है, बच्चे जाकर उनसे बोल देते हैं, अंडरस्टैंडिंग क्रिएट हो रही है। आपको घर से प्रॉब्लम तो बोलते क्यों नहीं हो सर से? प्रॉब्लम है ना घर से तो परेशान से तो बोलो। चाहे वो कुछ ना करें, एटलीस्ट उनकी उसमें तो रहेगा कि हाँ कुछ ना कुछ गलत हो रहा है, और क्या हो रहा है वो खुद आइडेंटिफाई करें। हम बुराई मत माया के केस में आप चाहते तो बचा सकते थे माया को। नहीं तो चाहिए किसी सबको फंसा सकते बचाने के लिए।
तेरे पैसे ही पकड़ी सी गलती
कर दिया है ना, तो हो जाते हैं कभी कभी। गुड मॉर्निंग। पी रही थी मैं। गुड मॉर्निंग।
ब्लड दे के आओ।
पट्टी में वो पैटर्न मांग लेती हूँ, वो पट्टी उतरवा लेती हूँ। बैठ के बना
Good
पट्टी का
afternoon, everyone.
पट्टी
This
उतार
is
दो
the
बैठ के।
second session.
और हाथ में
Please,
दर्द कर रही है
please mute your mics.
भाई, वहाँ क्या करेंगे?
Please mute
कोई
your
बैंडेज तो ले
mics.
लूं?
Please mute your mics.
ऐसे लेना पड़ेगा ना मैम। इतनी मेरी बात
Dr.
समझ नहीं
Deepika Arora, please mute your mics.
ये बैठ के आराम से काम कर रहा है।
Hello. It is a common platform. Please don't share your noise.
अविनाश ये सेशन सुन लो।
Dr. Deepika Arora, please mute your mics. It is not a good.
अच्छा नहीं ये सेशन ही तो मुझे सुनना है बस।
Please mute your mics. Everyone.
ये पूरा मेडिकल ओरिएंटेड है ना, माइक्रोबियल उस पे, मेरी पीएचडी उसी पे है।
Okay, please mute your mics. All mics. So good afternoon, everyone.
गुड आफ्टरनून।
Please mute your mics. Up. Otherwise, it is a rebound. Good afternoon, everyone. So this is second session of today. There is a very interesting talk from Professor Jasnendu Giri, Associate Professor, Department of Biomedical Engineering. He did his PhD from IIT Bombay in Department of Metallurgical Engineering and Material Science. After that, he has 3 postdoctoral fellowship from California Institute of Technology, National Institute of Artisan and Molecules Skin Disease, and National Institute of Standard and Technology. So he has many research publication with H index 18, and he has 7 patent. With that, he has working the biomedical engineering. I request him, Professor Giri, to give a talk on the nanotechnology-based antimicrobiology surface. Welcome to Professor Giri for his talk.
हेलो,
Please
गुड आफ्टरनून
mute your
बेटा।
mics. Deepika Prasad, please mute your mics.
हाँ बेटे, मैं खुद ही ट्राई कर रही हूँ। एक्चुअली डायरेक्टर सर इज ऑन लीव टुडे और मैं कंटिन्यूस 2 बार उन्हें कॉल कर चुकी हूँ, अभी उन्होंने मेरा फोन रिसीव नहीं करा। मैं बात करके तुम्हें अपडेट करती हूँ। हाँ, तुम परेशान मत हो, मैं शाम तक तुम्हें कुछ ना कुछ अपडेट करती हूँ। ठीक है? ठीक बेटा, ओके।
So I request Professor Giri to start his talk.
अविनाश, हाँ अभी देख लो, अभी हम होते तो हम दौड़ के जाते। नहीं देख सकता अब एक कोई नहीं हिलेगा, कोई नहीं हिलेगा।
चले जाना ऑडी में एक बार
नहीं, वो जबकि लंच ओवर हो चुका है, बच्चों को कायदे से बैठना चाहिए। What is going on?
Hi, can you hear me?
Yes, please. Professor, please carry on.
Thank you, Dr. Vibhu, for the introduction. So someone actually, I think someone is talking, still talking. Can you please unmute your mic,
अमन
please?
देख के आओ, एक बार जरा देख के आओ जरा किस क्लास में ये चल रहा है.
Why you are talking this, Deepika Prasad? Do you think you are very smart?
Maybe he cannot hear. She cannot hear the things. Maybe you can call her and ask her to mute. Okay. So, good afternoon, everyone. So today, actually, I'll discuss some of the, I think, some of the very interesting topic. So far, actually, I think it's the second day for your workshop, and then maybe one has covered it, or maybe entire workshop one cover. So I'll discuss very interesting topic which is relevant to your healthcare. Many of the healthcare related issue what the society is facing, or maybe will face for next 20 years, 20 years. So that part actually I'll discuss, and then there is a lot of research going on to overcome that issue, and some of the things I will discuss here. Also, we'll discuss in our lab some of the things we already developed and that commercialize. Also, I will discuss that part.
इनका काम इतना है, इनका काम इतना होता है.
Today, so Dr. Bibhu, maybe you can call her. Maybe she cannot hear what we are talking. So you can call her to mute her mic.
Sir, excuse me, sir.
Yes.
Sir, sorry to interrupt you. Actually, Dr. Deepika ma'am ko, I think you have the authority to please kindly remove it. It's better.
मेरा बंद हो गया क्या?
You kindly remove it.
मेरा
So
भी
it's
रखा
better
था.
for the other participants. So we can concentrate on your topic.
Bibhu, Dr. Bibhu, can you do that?
Sir, who have authority, they can.
Sir, excuse me, sir. The person admin can disable all the mics, sir. Please do that. Otherwise, remove that person.
कंफर्टेबल लग रहा है. एक्चुअली वो हट गया ना.
I cannot do. I think Dr. Bibhu, can you please do it?
देखे जरा ये मेरा भाई क्या कर रहा है. चलो हाँ, उन लोगों के सामने से नहीं निकलेगा.
Because I'm not, I can't see that. Maybe admin will
होता है.
डॉक्टर ने ये कमर उड़ाया नहीं सही, मतलब नहीं रिकवर हुआ, फिर एक इंजेक्शन लगाया फिर रिकवर नहीं.
एक बच्चा अपने आप में होता है. आप किसी को जीवन दे रहे होते हो.
तो पापा कह रहे थे मुझे साइन करवाने के लिए आए, डॉक्टर तो मेरे को साइन नहीं कर पाया था. करवाते हैं ना. कह रहे मैंने सूर्य दिया तो बोल दिया आप ही कर दो.
just one minute. Sorry for.
पड़ जाते हैं.
से किसी और का आ रहा है. एंटी माइक्रोवेव सरफेस ज्योत्सना गिरी. यार सब कितनी अच्छी अच्छी लैबों में पहुंचे हुए हैं. छोटे मोटे लोग भी कब पहुंचेंगे मैम?
Can you mute her? Actually, you have, since you have shared the link.
No, actually the administrator is outside. So otherwise this nonsense. Why they are joining this faculty development program? I don't understand.
She cannot listen what we are talking. So that is the reason maybe she is not.
They don't have common sense at all. There is a common platform, and they are talking to each other.
Ask your admin to mute her.
Okay.
Now she mute. Okay, first class. Okay. So sorry for inconvenience. And anyway, today we'll discuss one of the very interesting things, maybe a little bit away from whatever you people will be will listen that next 3-4 days. So this is little different. And since one of the topic in my research, so I thought of giving some shares of some of the knowledge on that topic, and then I hope you will enjoy it. So, well, before today talk, actually, we'll discuss some of the very interesting things. What I said, like the that surface, self-disinfecting surface. So when we are in the COVID era, and we used to with the regular disinfecting surface and different hands, your different surrounding surface, common touch surface. So as we know that there is chance for the COVID can transmit from the surface to you. So that is the one of the not only COVID. This problem is exist, and there is a lot of issue in the society deal this problem. So today we'll cover the microorganism which is basically responsible for different type of diseases, and we'll also briefly describe the common problem which is called the healthcare associated infection. That is one of the major burden to the society, and we'll discuss some of the bio-inspired antibacterial surface or an bactericidal surface which is exist in the nature, and we are from learning from the nature to create similar type of surface so that it will be more effective and more sustainable. So different type of self-disinfecting material we normally currently using or under development, and how it's work. And then we'll discuss some of the you also know many people that you also know that there is a bacteria, drug resistant bacteria is the surrounding environment, that actually that how we can overcome that bacteria resistant drug resistance using the nanomaterials as a novel nanomaterial system. Also, we'll discuss finally, this is Durokia technology. The technology is developed in my lab, and it also commercialized. It's available for the common use. With that, I'll move forward. So microorganism, some of the people already from the biology background, those are not from the biology background, not a problem. Microorganism, that means it has size as micron. So that is because our hair size is 200 micron. So now actually if you consider the hair size and then the organism size, that is you can consider that tiny organism you can have. This is called the microorganism. Sometimes this is 4 different type of class actually can classified. One bacteria, fungi, and protists, which is basically come the protozoa type of the category, and one cell eukaryote, which is the another type. And there is a virus actually, it is not considered as the microorganism because it as such it does not have it is not live or living. It is always active when it transmit to the host body. So these all the different category come under microorganism. Under this different category, you can have the 100 different type of pathogenic microorganism which is already causing lot of diseases, like one of the Zika virus, HPV virus, then you can influenza virus, the virus, hepatitis virus, many of the virus, coronavirus. So all the virus you already know. Now this is the all pathogenic it's called microorganism, but the virus actually, as I said, this is not live one, so it is not directly considered as yes. And then different type of bacteria, you can see these are the bacteria, different type of protozoa and other things. These all the pathogenic microorganism is causing the disease to us. Now that giving the on the length scale, how big they are, then virus normally it is the smaller in size. You can see this is the 1 nanometer, which is the atom, 0.1 nanometer, which is 1 angstrom, which is the atom. Any of the atom you take, this is the size. You can fuller in molecules, which is the C60 carbon ball. You can see is a nano ball, is a 1 nanometer scale. Lipid, whatever lipid actually we are eating, or that is size actually around 1, 2 or 3 nanometer. The protein, whatever exists in our body, that is also come under 1 to 10 nanometer within the below 10 nanometer. The virus above the 10 nanometer or within the 100 nanometer or surrounding 100 nanometer. You can the coronavirus come under this range 100 to 200 nanometer. Now the flu virus, you can see. Then you can bacteria, it is 1 micron, which is consider our hair, depending on the what type of shampoo or how genetically different your hair. This is the diameter of hair is varies from 100 micrometer to the 200 micrometer. That is, bacteria is, you can consider the bacteria size is 1 micrometer. Now mitochondria or in our cells also similar size. Red blood cell, which is carrying the oxygen, this is the micron, 1 micron to 10 micron, under 7 to 8 micrometer. Then plant cells above 10 micrometer, animal cell also 10 to 100 micrometer. Then pollen, which is the cause lot of allergy, so that is of size 100, above the 100 micrometer. You can see the, you can naked eyes, you can see the pollen. Naked eyes, you can see the your hair. So so these all the size you can consider. So giving the size aspect to understand the subject very well. So normally 100 nanometer, normally you can use the light microscope. Microscope means which is operate under light, like a fluorescence microscope, optical microscope. Here you can see there is a typical, depending on the what type of light using the microscope, that resolution, or you can see that object under that particular instrument. Like light microscope, you can see the with the top nose light microscope or confocal microscope, you can see visualize 100 nanometer object also, with the some assistance of the some fluorescence, other things. Even like the below 100 nanometer, if you want to see something, some object, you have to use the other type of microscope, which is the electron microscope, where the instead of light, you use the electron beam to visualize the object. Anyway, so that is the different type of microscope used to observe or visualize the different types of objects, starting from 1 Armstrong to the 1 millimeter. Now, before moving to the subject, I want to give the broad idea what the bacteria, like we can talk a lot of bacteria, drug resistant bacteria. The bacteria, normally it is if you consider the cell, our body cell is the lipid membrane, the outer membrane called the cell membrane, which is the lipid, the double layer. But bacteria membrane actually it will different than our cell membrane. So this is the typical bacteria. Here you can see the cytoplasm is there. Then genetic material is the DNA also there. Then also mitochondria and everything also there. Ribosome, everything is there. Then also is covered with the membrane called the bacteria wall or bacteria membrane. Now that you can see that the based on the structure and then structure of the membrane, the bacteria is classified two category, called the gram negative bacteria, gram positive bacteria. Gram negative is bacteria normally is E. coli, and gram positive like there is a different type of other bacteria there. You can see there is a bacteria membrane or bacteria wall. Membrane wall is there is gram negative. There is a 3 layer. One actually is phospholipid outer layer. In between there is a glycoprotein type of membrane, like the layer, and below there is which is attached to the cytoplasm. There is another phospholipid membrane. So you can see the gram negative, gram positive is different. The proteoglycan membrane is the very thick, 100 nanometers thick. Proteoglycan membrane is thicker than gram negative, and then there is a beneath that proteoglycan outer membrane, there is actually below there is a phospholipid membrane. Even like the other bacteria, which is the causing the TB, the mycobacteria. Mycobacteria also there is a membrane is different than other. You can see this is a proteoglycan and then lipid membrane. Also there is the specific molecule also exists in the outer surface of the membrane. So depending on the bacteria types and things, there is the bacteria membrane structure is different. Even like you can see the similar way, you can coronavirus. The coronavirus, even like that, there is, I think everyone knows that is basically virus having the genetic material. The single strand RNA is there inside, and then this is called genetic material, and this is coated with the envelope. This is envelope normally made by the envelope protein and lipid, envelope protein and lipid, and there is a different type of surface protein also there, which is the glycoprotein, or called the spike protein. And that using the spike protein, they can attach to the human cells, and that way they can get into the human cells and then infect the human. Now this is the structure, because the broad, I'm just giving the idea that all the microorganisms having their membrane, which is made of phospholipid, made of the protein, made of the proteoglycan, and the different type of, that is the membrane actually exists for all microorganisms. Now, the question is, the bacteria, I think many people already, you know that there is a drug resistant bacteria. This is called the MDR, multi-drug resistant bacteria. So when you go for this is the one of the threat to our society, threat to us also, because there is a many type of antibacteria antibiotics exist, because there is a different generations. You can see anything's actually happened, doctor give the antibiotics. This is not the good practice, because more you give the antibiotics and more there is a chance to bacteria exposed to the antibiotic and that grow their resistant. So that is called the bacteria resistant. So drug resistant bacteria. That means whatever drug you are using, the exist in that our treatment, that drugs no longer is response to the bacteria. This is called the drug resistant bacteria. So drug resistant come from the different. There is a different mechanism how the bacteria can make the drug resistant. But many of the things, even like that, there is a different process where the bacteria when sit on the surface and then make called the biofilm. So when the bacteria is alone, the single bacteria, they just attached on the surface. Surface may be your hand, surface may be any surface which is surrounding the patients. Hospital, I will come to there. We'll give the more discussion. So any surface, the bacteria fall on that surface. There is alone. They are empty. Surrounding is empty. Now they attached on that surface. That is called the attachment. And once they adhere the surface, they start to grow. Then once they grow, they secrete the different type of molecule to coat or surround them. This is called the matrix. So these molecules is the polysaccharide, many of the polysaccharide, and then glycoprotein, different type of molecule, the compositions exist, mainly polysaccharide. And that you can see this is the bacteria is no longer is like the naked. It is just covered by the different type of molecules. So that call this type of stage, this stage called the biofilm formation. That means if you use the drugs, that drugs will not directly attack to the bacteria. That drug first need to penetrate to the matrix, then it's come to the bacteria when it should come to the bacteria surface in the cell membrane or whatever, then only the bacteria can be killed. Other than that, if this drug cannot penetrate nicely from the periphery to the inside to the biofilm, then that way actually the bacteria cannot be killed. So that most of the issue come from that treatment or the treatment modality is the issue is when the bacteria make the bacteria film formation. This is called the biofilm formation. The inside the biofilm, the bacteria remain very dormant stage. Like whenever that needed, they expand again, and then they become opportunist. And here you can see that whenever they needed, they come out, and then they can grow surrounding and then give the symptom. So this is the biofilm formations. When the biofilm formation happen, that is very difficult to treat. And most of the cases, drug resistance come due to the biofilm, because biofilm will not allow the drugs get inside. That will bacteria, even the doctor give the bacteria like the antibiotics for treatment, but the bacteria will not completely kill because it remain within protected with that matrix. So this biofilm killing the bacteria is very difficult. So considering that one of the way that bacteria become drug resistant. Now considering the scenario, drug resistant bacteria and then associated death, there is a huge burden to the society. It is expected that now actually almost 7 lakh of death happen due to the drug resistant bacteria. That means whatever drugs available in the market for the treatment, that drug it not responds to that killing the bacteria. That means this is called the drug resistance. So that related death actually now actually it is 7 lakhs across the world. Now it is expected that it will go to the at least 10 million by the 2050. That means you can see there is on the projection. There is a different region, Asia, that the death will come from the drug resistant bacteria. The death related to the drug resistant bacteria. Okay, now the question is how these type of things actually can be overcome. So taking considerations of the situations, that drug resistant bacteria, their associated infections, and then the transmission of the microorganism from the different surface surroundings, and then actually what is the concept come the self-disinfecting surface or long-lasting hygiene products. So why? Because you can see that bacteria, many of the bacteria, virus, pathogens, whatever you can say, they can survive on the surface from the starting from the few minutes to few hours to the few days. Even they can survive in very hostile environment. That means dry, heat, everything. They can survive on the surface. So that bacteria or virus, pathogen, fungi, whenever people touch, and then somehow actually it is come to the infection and then cause the disease. So there they can survive the surface. Surface may be the hand surface may be the your common touch surface surrounding the patient surface surrounding the hospital, and then I'll come there. I will discuss more details. And surface may be the implant surface. That means many of the people having the implants, dental implants, that your many of the biomaterial implants is there, dental, knee, many of the implants is there, that surface. So bacteria, they once they make the film, then definitely it will not, you cannot kill them by using the systemic drugs and things. So that is the reason, if you can make the surface self-disinfecting, that means when the bacteria fall on that surface, that point the surface can work on the bacteria and then instantly kill. That is called a self-disinfecting surface. So that is the one of the possibility to overcome this type of drug resistance or the bacteria or the pathogen transmission related death. Okay, so now how one of the major issue in our society is the hospital acquired infection. I think most of the people knows that any patients went to the ICU, there is a high chance that even the patient went to the ICU for some sort of cardiac issue. There is a high chance that when patient goes to the ICU, then there is a 30 to 40% chance that the patients end up with that infection. The infection comes from surroundings. So this is called the hospital acquired infection. Normally, any type of people, any patients go to the hospital, there is a 10% chance that patients come with the infections from the hospital. If this patient get into the ICU, the statistics shows that there is 30 to 40% chance that the patients get the infected from the surrounding environment of the ICU. That actually is the secondary infection, which that is the cause of the death, not the patients went to ICU for the some of the disease. That disease can be cured. Actually, that with the stay of that ICU, the patients actually infected with the drug-resistant bacteria or virus or pathogen. So that actually it will be this type of this is infection called the hospital acquired infection. How it's work? Let's say patients having, let's say, some of the TB. Now the patients, their biological fluids like saliva, many things, and then they are contaminated to the surroundings environment, like beds, the associated instruments, and then maybe the beds. Now the doctors, nurse, they come touch the patients, touch the surroundings, touch the instrument, and then basically, or doctor, maybe the patients coughing or sneezing, then all things actually that contaminated the surrounding surface, by that pathogens. Now even like the doctor, nurse touch to the surroundings, that also contaminated their hand, other things. Now when this type of contaminated surface, like the, let's say, door handle, many things in the ICU, then this ultimately the pathogen which is present on the instrument surface, surrounding surface, doctor, nurse's hand, then they touch to the another patient which is in the ICU or hospital. Now this bacteria pathogens is contaminated to the another patients, where actually initially it is not she or he is not contaminated with that particular bacteria or pathogens, whatever is the other patient having. Now that way this chain actually keep on going. This is called the hospital acquired infection, which is 40% chance of the patients when get into the ICU, there is a 40% chance that they come with the the hospital acquired infection. So this is a major burden to the society. Now that you can imagine that surface, that maybe the hand surface, maybe the surrounding surface, maybe the instrument surface, maybe the many of the implant surface. If you make the cells disinfecting, that means when the bacteria or pathogens or virus they fall on that surface, that's instantly or they kill with the time. So that is called the cells disinfecting material. Now there is a different type of disinfecting materials if people are working on it, or maybe some of the things is already in the clinic. So there is most of the things is under research development. So some of the self-disinfecting materials is known as the silver, gold, zinc oxide, titanium oxide, and many other material. Where actually this type of material they release the silver ion, silver ion, and then also zinc, different ion. Also they release the ROS, reactive oxygen species, to the surrounding or to the vicinity of the bacteria pathogens when fall on that surface, or in presence of light, particularly titanium oxide, zinc oxide, they are basically photosensitive. And when the lights actually UV lights and lights actually fall on that zinc oxide or titanium oxide surface, they create the ROS, reactive oxygen species. So reactive oxygen species actually, reactive oxygen species basically they actively kill the virus, bacteria, pathogens by the oxidations of the different type of cellular molecules, membrane, cellular molecules, protein, lipids, DNA, RNA. So that way actually they damage and that bacteria pathogens will be killed. So I'll come to some of the details. And there is another class of disinfecting material normally we commonly use in the household or many purpose like the Lysol or different similar type of disinfecting material. This consisting of the quaternary ammonia compound. 1 minute. Sorry. Okay. So quaternary ammonia compound. This is the this is quaternary ammonia compound. You can see this is the quaternary ammonia compound composed of the. You can see this is the nitrogen and there is a 4 alkyl group, which is the resultant charge of the nitrogens is the positive charge. This is typically structure for the quaternary ammonia compound. Like the one of the very common quaternary compound actually the citramide. Citramide, which is used in the Dettol. Dettol actually, this is the content of citramide, chlorhexidine. Benzalkonium chloride, which is the BKC, also very commonly used. Hello? I'm in talk actually, so can you please call after sometimes? Okay, so benzalkonium chloride, and then different type of quaternary citramide. This is the quaternary compound. Is the very known. How it's work? So the quaternary compound actually also cell membrane they lyses the or make the hole in the cell membrane of that bacteria or virus. That is the reason actually extensively benzalkonium chloride is extensively used for the household. Like the Lysol contain the nothing but the benzalkonium chloride or similar type of floor cleaner, and this is typically contain the benzalkonium chloride or quaternary ammonia compound for that purpose. Now there is also there is different type of nanotopography or microtopography surface also under research to make the cells resisting material. Now we'll come to all the details. The question is where
Professor, it is now. Hello.
Yeah.
This PPT is
not
visible.
Okay, 1 minute. Something I don't know why actually. Sorry. Now it is visible.
Yes, yes. Please.
Okay. So what is the time now? Okay. So now actually see, this is the question is how, where people learn that self-disinfecting surface properties. Now they learn from the nature. So people first found that cicada is the, you can see these flies wing having some particular feature on their wing, that this is called the that cone type of nanotopography. So nanotopography means nano cone structure on their wing. You can see this is the wing consists of this type of nano pillar. So the cicada wing, if you put the bacteria on that cicada wing, the bacteria cannot survive. So it will, the typical wing, you can see the 200 nanometer heights and then 16 nanometer diameter in the top and 100 nanometer at the base. So this is the cone type of structure in the consisting of the cicada wing. So many of the flies having the similar type of structure is there. Now if you bacteria and fall on that surface, the bacteria cannot survive. I'll come there. Now not only that flies, many of the fish, this is the sea fish, and even like the sea fish, and also there is what is called shark also, shark skin, they are having this type of feature, nano micro feature, that also surface act as a antimicrobial in the surface. That means any bacteria, pathogens or cannot survive on that surface. So that way they can overcome from the any infection from the surrounding pathogens. Even you can see this is gecko. So this is, you can see it has also skin has the particular feature, show the topography. Even you can also know that there is naturally occurring like the lotus leaf. There is also that is super hydrophobic. That means any type of the hydrophilic materials like the bacteria, even like the water. If you fall there, they're so hydrophobic that will not wet. That means that way it acts as a self-cleaning. That means the dust, anything cannot attach on the surface. This is because surface is so hydrophobic and so low energy, so that anything material will not attach on the surface. That means it acts as self-killing or anti-fouling material, so that the any pathogen something will fall under there will cannot attach. So from the nature also, people trying to understand how what the mechanism is following or happening, so that the surface become antimicrobial. So there is two type of things actually in the nature we found. One, called the anti-fouling surface. Anti-fouling surface means that any pathogens will not attach on the surface, because as I said, the first interactions of the pathogens, bacteria, virus, anything, it should be attached on the surface, interacts in surface and pathogen. Now anti-fouling means the surface is so super hydrophobic. Hydrophobic means, if you some of known from the physics background, hydrophobic means there is a super low energy, surface energy. Any surface having low energy, there is very difficult to make the interaction. So that way is called the anti-fouling surface. So any type of pathogens, bacteria will fall on there, it will repel, it will not attached on the surface. So if it will not attach, then definitely it will remain clean. And that is anti-fouling. It is exist in the lotus leaf and many of the leaves where you can see that this is super hydrophobic. You can see this is the leaf, different type of structure from the leaves from the nature. You can find out this is the water droplets. You can see this is not wet. This is called the anti-fouling. In similar way, the water or many things actually, let's say you cough or you sneeze or something, your droplets. Like the droplets contain a lot of pathogens, will fall there, it will not attach and it will clean up from the surface remain clean. And also there is called the nanostructure or microstructure surface, where I have shown that cicada wings and gecko and then other things, other wings, and then the fish surface, they are having the nanostructure or microstructure on the surface, which act as a biomimetic mechanobactericidal surface. That means this I will come there, where actually the bacteria on that surface, the bacteria cannot survive. So that is called the mechanobactericidal surface. Well, so some of the surface having the both, some of the nature having the both. That means it acts as a antifouling as well as the mechanobacterial surface, mechanobactericidal surface, and also people trying to develop the surface having the both properties. So there is some of the lot of research people trying to understand how this bactericidal surface, which is exist in the nature, work or kill the pathogens. So there is a many of the so normally it has shown that the mechanocidal properties of that surface or the killing properties of the mechanocidal surface is depend on the size, shape, or aspect ratio as well as their distance between the different type of feature. That means if you have cone, that is the aspect ratio difference. If you have rod, this is the aspect ratio different. If you have this type of structure, so this is also their mechanical flexibility rigid, whether this flexible or rigid. Also there is a spacing, the spacing between this type of feature, like as I said, there is in case of cicada, there is cone type of structure, nano structure. So how the spacing between the different cone structure, that is all matter, and then it's reflect how fast or how effectively kill the pathogens when fall on the surface. I will not go to the details. So that one of the example you can see that all the naturally occurring the or mechanobactericidal surface is contain their, if you consider heights of the feature, that nano structure or spacing, and then their tip diameter, everything come within the range. That means it is within the 1 to 100 500 nanometer scale of their spacing. Height also it is around 300 400, also their tip diameter, everything. But people trying to mimic that structure by that laboratory, in the laboratory, different method like top down approach, bottom up approach. So I'll not go details. Many of the many of the people will discuss that different type of synthesis technique. I'll not discuss today here. So here you can see people try to make that similar type of structure by the actually matching that type of biomimetic feature. So but still actually there is very difficult to achieve in the bulk scale. So what is the mechanism how that surface act as a antimicrobial or bactericidal surface, bactericidal properties? So normally nanoparticle mediated the antibacterial, there is a 3-4 mechanisms involved. One, that nanoparticle, those are very free to get inside that cells, bacteria cells. So normally when the nanoparticles interact with that bacteria surface, nanoparticle may be the rod, maybe carbon nanotube, single one carbon nanotube, multi-wall carbon nanotube, gold silver nanoparticle, gold nanoparticle, zinc oxide nanoparticle, many of the nanoparticle, whatever you can see, this nanoparticle, when they come contact with the bacteria, and this nanoparticle actually make the hole on the surface. If you use the appropriate surface properties of the nanoparticle, they make the hole on the, create the hole on the surface. So this hole actually, once they make the hole on the surface, or maybe that nanoparticle get inside the material, bacteria or something, they interact with the different other cellular molecules and then create the ROAs and many things. So this is basically the physical rupture of the membrane as well as the interaction with the cellular molecules. That way actually they can, internalized nanoparticle can kill the bacteria or pathogen. Now those are in the feature, surface feature, which is the similar to the cicada wing. Then they basically make there is a different mechanism they follow. So in this mechanism, here you can see this is the wing. When this type of structure bacteria fall on that surface, the bacteria actually they poked by that they poked by that feature, nano feature on their membrane, as I discussed, that bacteria membrane, the poked, and that actually the poking, it make the lot of stress to the bacteria, and or pathogens. So that way they cannot survive on the surface. This is called the mechanobactericidal properties. Also there is if this is there is not the uniform feature, there is a bigger, smaller and things. There is also not only stretch on that membrane. There is also other mechanism which is the also exist. Normally this is the based on the mechanical disruptions of the membrane to kill the pathogens. Similar way also people trying to develop something, because all the mechanobiological properties or mechanical destructions or physical destructions of the bacteria membrane takes longer time. So people try to make the more faster killing using the rod or cone or different type of structure with the zinc oxide, zinc oxide or copper. So zinc and copper, as I already discussed, the zinc copper has their own property, create the ROS, reactive oxygen species, in presence of light. So that the mechanical disruptions with the ROS is make the faster killing of that pathogens on the surface. Anyway, this is the overview. This is how the research actually keep on going. Try to understand how they are trying to model that membrane of the different bacteria, pathogens, and then when they interact with the surface, the different stress, different stage in the membrane, different stretching in the membrane, so that mechanical stage or stretching actually make the how they're killing the pathogen. That is not people trying to understand. So far, actually, you can see there is synthetically people make the zinc oxide, by wet chemistry, copper oxide, zinc oxide, different type of zinc, copper, and silver structure, different type of surface structure, where actually that they check with the different type of bacteria, gram-positive, gram-negative bacteria, killing efficacy. You can see the 58%, 70%, 90%, 24 hours. It takes longer time to kill, 1 hour to kill. Then also people try to make the PMMA. PMMA, like the one of the very common polymer people use, polymer based material, make the surface with the different type of nano or micron feature on the surface using PMMAs, different type titania, and then make the different type of structure. Here you can see silicon and many things actually. Some of the things is understanding that how it's work on that bacteria pathogen surface. Some of the things actually try to make the commercial scale so that the surface can be make the antimicrobial or self-disinfecting. Here some of the things actually I already tabulated. Here you can see different feature and different things actually it is there. Many of the literature actually there's a nature review I took from, and you can the gold base the surface people can create nano air, nano pillar, nano things, and titania surface, because titania is the one of the important aspect, because titania is extensively used as a implants. So like the tooth implants, many of the orthopedic implants, the titanium is extensively used. The titania surface, if you make that nano feature, that surface become the antibacterial. So that means that way actually it will not the many of the implants is failure due to the bacteria infection, and then that is the once the bacteria actually sits on that titania surface, then make the film formation, which is the biofilm. Once the biofilm form, then systemic if you take the antibiotic, will not work. So ultimately that failure, it will the implants will failure. Now the doctor need to re-implant, remove the things, re-implant the things after needed. That is also again expensive procedure, other things. So that is the reason titania and different surface where you can make this type of feature so that it surface become antimicrobial, so that there is the implants associated infection may not come, and then that way. So you can see the cardboard people use carbon nanotube, graphene, many things actually we're trying to understand to make the similar feature on the different surface. So some of the example I'll give. So zinc oxide, where actually people prepare the zinc oxide rod type of material, and that zinc oxide rod prepare synthetic wet chemistry methods, and that actually can be coated to the different substrate like the titania, ceramic, silicon, zinc, and glass, many things substrate, and try to when you code, then surface looks like. And if they are trying to understand how fast they are killing the different type of bacteria and how they are killing, as I said, that is mechanical disruptions of the membrane, one of the mechanism when you make this type of mechanical structure or nano topography or microtopography. Also zinc and zinc, copper, and they have their they can exist in the both stage, like the zinc plus as well as the zinc atom. So that redox system actually create the reactive oxygen species, like the superoxide. You can see superoxide on that, on the surface, zinc oxide, zinc, there is a substrate, and then that create the superoxide radical when in presence of bacteria. That radical also help to kill that, so that the overall killing mechanism will be the faster. So similar way, people try to develop the zinc and zinc core and zinc oxide surface to make the redox system. So here you see this structure, the zinc surface, the particle, nanoparticle, it is having the micron particle, that where the core is zinc and the surface zinc oxide, but the surface having the different type of zinc oxide cone structure. So this is the nano feature on the surface. Also zinc in core and zinc oxide surface that create the redox system. They create the any point in absence of light also they can create the superoxide. So hydrogen peroxide, superoxide, and that hydrogen superoxide, when the bacteria falls on, pathogens fall on that surface, then that actually in case of the mechanical destructions also as well as the superoxide that kill the pathogens faster way. Here you can see the different E. coli, Asorias, and different type of bacteria they checked, and then the killing efficiency with the time actually they checked. So this is very recent literature, and the people also trying to develop copper oxide. The structure having the rod copper oxide structure. Also, this is the blade type of copper oxide structure, copper hydroxide, copper oxide tube, nanotube, and the nanoblades, copper oxide nanoblades, and copper hydroxide nanotubes. And then that can be coated in the different surface, so that they check with how effective the killing the bacteria is, so that the surface actually becomes self-disinfecting. Also, people trying to develop that bandage material. Bandage material, you can normally bandage actually for bandage cotton is used. Now the bandage material coat with that this type of nano particle, like the whatever zinc oxide core cell structure, the coated with that bandage cotton gauze, and that surface become this type of cotton gauze surface become this type of feature, and then that actually that cotton gauze is used as a dressing material without presence of the any antibiotics. So that is help in that bacteria killing. Even they tested with that, they introduced that different pathogens with the Asorias in that wounds, and that dressing done using that cotton gauze coated with that particular nano feature material, and then they have their they can check that can kill the pathogens or bacteria without using any antibiotics. So this is going on. Now the question is, now people trying to, as I said, there is another issue, that drug resistant bacteria. So drug resistance bacteria is one of the major issues. Drug resistance pathogens or drug resistant mainly bacteria is one of the issues. Now people learning from the nature, people trying to make some sort of nanoparticle based antibacterial which should work selectively for the bacteria. Now the one advantage is, one of the example I took from the nature, which is the published in the 2020. So here you can see the model particle people created. Now scientists created model particle to understand whether this nanoparticle can be effectively kill pathogens or bacteria, or may not, it should not the toxic to the normal cells. So nanoparticle, this is silica nanoparticle, and that is the decorated with the different type of polymer brush. Polymer brush nothing but this is the some of the few of the polymer which is the attached to the surface. So here you can see hydrophilic nanoparticles. Here you can see the hydrophilic nanoparticles, silica nanoparticles, then coated with the different type of polymer brush. So this polymer brush is, this particle will be effective to kill the pathogen like the bacteria, or they make the pore on the surface in the different pathogens bacteria, but it will not toxic to the cell. Because one of the important aspect you have to look into, the even this on that surface, I think that I just want to mention something. So even like different implants, there is another issue is implants, when you put the any implants, let's say titanium implants for your bone, hip joint. So that metal actually implants in the hip. Now that the implant, once the implant, there is a bone cement is used. So initially that they act as a similar type of cement. That use the cement, and then that implants actually the whole joint actually hold with your leg and then hip. Now that cement, if strengthening that joint, like the holding that implants. Now that with cement, now for permanent integration, you need to the surrounding tissue like bone tissue should be grow on your attached on that implants. That is one issue. That is the you have to attach or strongly bind to the surrounding tissue, otherwise you are jumping or is loosening when you jump or something, then that is your implants will loosen. So that is the one of the integration of the bone or surrounding tissue. The implant is the one of the major objective for any of the implants or our biometal implants society. We are also working in the similar field. So that also try to understand how you can integrate the different tissue, surrounding tissue like bone on that implants. So that also people try to understand. So it is shown that the nanostructure on that implants help to the integration. Now another view is nanostructure, it kill the bacteria. So this is the advantage both way. One nanostructure, if you make the nanostructure on that implants, that help to the stem cell to grow and then integration. But that nanostructure particular feature, if you make, that will kill the bacteria. That is one of the good things. So why this happen? Because our cells membrane is much more flexible. That means it can deform on that nanostructure surface. So it will remain non-toxic to our cells. But when bacteria, other things happen, their cell membrane is the rigid in nature. That is the reason it cannot deform, and that way it's make the hole. That way the nanostructure, or if you can see the nano polymer brass and other things, it will make the hole on that bacteria surface, but it will not make hole on your cell membrane. So that way it is not toxic to the cells, but toxic to the bacteria. One of the this particle shows that this particle non-toxic to the cells, but it's toxic to the bacteria. They have tested the different pathogens and things. You can see the cell viability. That means if you culture that cells with that presence of the particles, that particles actually it's non-toxic. That means cell survive or remain viable 100%. Now if you put that one into the bacteria, then actually it is, you can see the MIC value. That means the which is the concentration where the bacteria killed happen. So 50% bacteria kill happen. So or bacteria growth will not happen. So this is, you can see the when the particle size increase, that way actually smaller the size is the higher the effective for the antibacterial properties. Now the with increase the size is the antibacterial property decrease. Anyway, so it is there. They have model. They make the model membrane using the liposome and then other things, and then to understand how these particles is create the hole on the membrane. So in the bacteria, with this membrane actually mimic to the bacteria membrane, but it is not make in the hole on the cell membrane. So that is the one things actually trying to understand from the nature, trying to learn from the nature. The people try to develop the nanoparticle system, which is non-toxic to the bacteria cells or body cells, but is toxic or antibacterial property to the bacteria. So that way, that is the because that the membrane structure is different and that their flexibility or the rigidity is also different. That way, actually, this particle will nicely become antibacterial for that bacteria or pathogen, but it's not toxic to the mammalian cell. Now I'll come to the one of the things actually we have developed in our laboratory, and also we commercialized that one. So I'll discuss that part. So normally, so far we discuss which is under research and people trying to make in the large scales, not yet in commercial products available. Now that some of the you someone know that there is some sort of long lasting hygiene product also exist in that, maybe last 5 to 10 years it is exist in the market, which is normally people use the sealant based compound. Sealant based means there is a sealant silica and then polymer chain, which is basically that again the quaternary compound, ammonia compound is there, and silane, which is the OH group, SiOH, and there is some of the long chain polymer is there. Now this molecule is the molecules where actually if you spray on the surface, they attached on the surface, and then this is the long chain, hydrophobic long chains, and there is a positive charge, and that actually act as a needle. That is basically Juno and other company where actually you might have come across a long lasting hygiene product. Now the company is exist. This is they normally use the silane based molecule. That means the silane, if you normally water based formulation, if you spray, then there is actually OH group on the attached on the surface, and then they just arrange that way, and this the more polymer chains act as a needle. So when the virus pathogens fall on there, due to the hydrophobic nature act as a needle, they poke on the surface, poke on the bacteria and virus surface, and that the mechanically they lyse the or they break the cell membrane, and that way actually the bacteria or pathogen virus they lyses, and then that way they cannot survive. But the question is, it is normally water based because silanes actually it is the water soluble, and then it's take longer time, 10 to 30 minutes to kill the pathogens on the silane surface, coated surface. And this you can see the water based. None of the things actually it is you will not find anything in the use in the clinic, which is the hand sanitizer or surface disinfectant, which is not water based. So we started in our our lab started in that 2020 March, when that time actually it is pandemic started. We since my group also working on the different nanomaterial for biomedical application, we started to investigate because that time actually I was responsible to make the sanitizer for the surrounding hospital where the very crisis for the sanitizer. We IIT take the initiative to make the sanitizer, which is WHO approved for formula, and then we supply to the surrounding hospital. So that time actually I was the responsible. Then we started to think that, but the conventional, you can see the conventional hand sanitizer, surface disinfectant, keep on you have to use to protect, because every time you touch, you use your hand sanitizer. Every time people touch, you spray the something. So this is very actually, that is very laborious job. Then we started to think about it, something like the long lasting action can you develop. Now that time we started to dig out the literature. There is this type of, as I already discussed, there is some the product actually which is available in the abroad company, which is the Juno and other company, or 20 microbacterium Juno. They are actually that silane based compound they are selling, and this is damn expensive. And then also some of the research actually copper oxide and other things. And then that the scenario that the COVID can survive for longer in the surface, then people started to thinking that something actually because self disinfecting surface disinfecting material, or it was not so popular that time. Now actually since COVID can survive for longer in the air as well as the surface, then people start to thinking to develop some sort of material which can be commercially viable. That time actually you can see this is the copper. There is some of the product actually. After that there is product came out, and then that product this is the so here someone actually can you mute your microphone please? Okay, so so here you can copper oxide. There is something silicon based. There is a killing time of that virus actually 1 hour, more than 1 hour. Even like that, there is a specially formulated bacteria which is the longer action, but it is the take the longer 2 hours to kill. Now in that point actually we trying to think about it. So we need to develop something which is not silane, which is mainly actually alcohol based, and also it should have the fast action. That means you can imagine the COVID, if you have the virus actually fall on the some surface, high traffic common touch area where actually people every minute there is a lot of people touching, then there actually if your material actually take longer time to kill, that definitely that time period you will that surface can infect it, or the pathogen can transmit to the many of the people. which are touching in between. So we are trying to think about something actually we develop, which is alcohol based, also which can instantly kill that pathogens, COVID and other pathogens instantly kill, so that like it will be fast acting things. So we have the keeping that consideration that is the instant killing should be there. The formulation should be in the alcohol, even needed, that is water based also we can make it, and that can be used for the soft and hard surface, and that give the prolonged protection. Keeping that consideration, we started to research out. We started to research, and we developed some of the technique which is called the very innovative technique, the Durokia technology. So here what we did, we combine many of the known science, like you have known that sealant, they use the molecular needle. So where the needle actually poked on the surface and then things. Now, so far actually none of the product which is used the topography. So we try to make the topography. We develop the Durokia technology where I'll come to there. We have the very innovative nanoparticle system, which has surface as the different nanotopography. And now, which the particles, if you spray on the surface, it make the nanotopography. Also, the particle surface having the molecular needle, which similar to the sealant. Now, not only that, the particle contain some of the active molecule which can be released vicinity of the bacteria or pathogen, vicinity on the pathogen. That combining three, topography, which is the mechanically disrupt the kill the things, molecular needle also mechanically. Now also the release, also combining three, you can expect the very fast acting material. So this is the typical nanoparticle system where you can see this molecular needle is there. The nanoparticles having the properties where if you spray on the surface, they attach on the surface and make the uniform coating. That uniform coating give the topography. So I'll come there. Here you can see this come with the alcohol or water. Then once you spray or apply hand or surface, then basically alcohol, it instantly kill pathogen that act as a conventional disinfectant, that way they're similar. Now they make the nicely coating on the surface. That coating give the lot of like the nanotopography. Also the molecular needle, you can see this is the nanoscale to the microscale to the, so this is type of topography feature on the surface. Now any bacteria, virus, pathogens fall on there, then their vicinity also, there is some of the mechanism where actually that there is some active molecule also released in that vicinity. So combining three, you can expect that is any type of pathogens fall on there, and that way keep on protecting for longer, and that up to 35 days. So on that, we launches 4 products. So one actually called the Durokia S. Durokia S means alcohol-based surface disinfectant, which can protect up to 35 days. So it's longer that, but though you can spray the surface and make the coating, and then the surface remain antimicrobial or antibacterial, antiviral still the up to 35 days. Durokia H, which is H for hand. So this is a hand sanitizer. You can apply on the hands, and then that let it dry, and then your hand remain protective till 24 hours or your next hand wash. Now M is the mask, antiviral mask. So you have to apply outside of the mask so that it makes the similar coating. And then that mask actually, when bacteria, pathogens or virus actually fall on the outer surface of the mask, because many times what happen, the mask actually that it suggests that the mask is fluidically you change. It should not touch the mask outer surface, because the outer surface contain the pathogens, and then you touch that is from hand to it will be transmitted to the even like using the mask also will not effective. Now to make the antiviral mask surface, the outer surface you can spray on it and then let it dry and become it is soon that the coronavirus or COVID-19 can be killed within 1 minute of the interaction. Durokia H, this is basically H aqua, which is the foam, alcohol free normally for the alcohol sensitive skin, as well as the people kid, for the kid friendly. So the 4 product we launches, and that product launched by our education minister, which is Ramesh Pokhriyalji, 2020, 2021, and 16 April we launched the product. So as I said, like the once you spray this particle system, here you can see the SEM image. This is you can see this is the 2D image of the particles on the coated on the surface. Even the FM image, you can see this is the particle uniformly. And FM image, you can see there is a height, the mapping. You can see this lot of nano topographical feature actually is created. And that nanotopography also molecular needle you cannot catch. So molecular needle also in between there. So that whatever we discussed, that is we already proved, and then we checked like the we take the different efficacy using COVID-19, and then there's a lot of different formulas here. You can see that average time of killing is less than 60 seconds. So that means you can see the control and Durokia coated surface either S, H, aqua. Here you can see the control of control having that bacteria actually, the COVID actually, this is the number not remains same, but within 1 minute also the survival of that COVID on the surface is actually is 0. So here you can see 1 minute DKH, 1 minute 100% killing. DKH also DKS is surface disinfect 100% killing. Surface disinfect like the hand sanitizer also 100% killing, and then aqua also similar way. We also dig out lot of how the more further mechanism, as because this is our research lab, and we try to understand what is the molecular mechanism and things. We did a lot of study. We found out the similar type of things. Here you can see the E. coli Escherichia's. If you coated surface of the Durokia coated surface, you can fall. There is with time, even like there is within one minute with 100% killing of the bacteria, even gram positive, gram negative, gram positive. So now even like the control sample, you can see this is the within like 1 hour there is the bacteria on the surface remain alive. Also the control nanoparticle system where we didn't do any decorations. Also you can see there is a killing, but it is as similar as whatever people reported. Take the longer time. So other study like the will not got ROS generations and ROS like reactive oxygen species generations happen because on that surface when that bacteria fall on that surface, and then there is actually you can see the high amount of ROS generations happen, which is basically there is one of the reason actually it is killing the faster killing. Even there is we check the biocompatibility other things that remain. This is not toxic to the human cell, and then but is toxic to the bacteria. Also check with a lot of pathogens which is normally causing the different type of diseases. That is also shows the result shows that this is the different type of pathogen, fungus and things. Within 1 minute actually it's 100% killing is there. So same way different Durokia surface, and then also mask you can see we can also take the mask in the CCMB. We did that, rotate the mask surface with the Durokia M, and here you can see up to 1 minute and the 5 minutes incubation. 1 minute you can see this is actually almost 90 more than 99% actually killing of the COVID-19 happen, but in the control there is not killing. So virus remain alive. So that is the efficacy. So we did the extensive field trial. So because since as I said this is from IIT lab and things, so we did the field trial inside IIT where actually spray the our material on the different leaf surface, different common touch surface. We collect the sample periodically. We use some device to instantly check like how much bacteria on the surface. Then we found that you can and then many of the places where you can see the control having that bacteria growth is present, but different type of places where we collect the sample, most of the places there is no bacteria presence. So hand also we did the test in the different hand. Then you can see up to 6 hours people apply on the hand. There is one hand actually conventional hand sanitizer, other hand actually our Durokia, and they went for normal work. And then after come back different time interval, we collect the sample and culture on that agar plate. We found that whether there is any bacteria presence on the surface hands or not. We can see most of the hand does not have content of bacteria when Durokia. Aqua also similar result we found, and then you can see this is the product actually. Our real image of the product, which is Durokia range of product, which is available in the Amazon, which is available in the Flipkart, also which is available in the Kia Biotech. So I have two company. I have associated with the two company startup, which is Kia Biotech, which is who has launched the product, and there is a IFOCare, which is the research wing, of that different type of product, and that is basically this product looks like. If you please check with Amazon, Flipkart, also our website, and you can get the benefit out of it. With that, actually, I would like to thank everyone, and I'll be happy to. I guess I'm in the time. We'll be happy to take any of the questions if you have.
Thank you very much, Professor. Now it is the time for questions. If you have any questions, please ask to Professor Giri.
Good afternoon, sir.
Yeah.
Sir, in
And loud.
IIT Hyderabad, there are academic blocks ABC. So
Yes.
at the entrance, there are the sanitizer is arranged, sir. So my question is, these nanoparticles are mixed in that sanitizer, sir?
Sorry, I can hear you. What?
Entrance of academic blocks ABC, there is a
No.
sanitizer.
That is a normal sanitizer. No, we are all the lift and other common area. We are using our Durocare. IIT is using the Durocare, yes. But the hand sanitizer is the normal one, because that is the decisions from the IIT authority, because that is the since they have to buy and other things. So that is but our IIT, entire IIT, the surface disinfectant using Durocare.
Sir, one more thing, these nanoparticles are used. I came to know that when it goes into lungs, it will create a problem. So,
Sorry.
I came to know that if you are using more nanoparticle, if it is going into lungs, it will create a problem. So, by using this sanitizer with nanoparticles, will it not be hazardous one, sir?
So one thing, actually, I think you know that many of almost all the product we use, shampoo, many of the cosmetic, so all contain the polymer, some of the polymer. So you are using a similar type of polymer, which is extensively used by humankind. Understood? So
Yes,
that is anything we are using which is not used so far, like the not gold, not silver particle, not zinc or something. So we're not using. So you are using whatever is the exist or extensively used the human beings for the last 80 years, 90 years. So we are using that. So that way, actually, we are good to go.
Thank you, sir. Thank you very much, sir.
Sir, can it act against tuberculous bacilli? What is your...
Can you?
Can it act against tuberculous bacteria?
Yes. So yes, actually, we checked, because that is most of the pathogens we tried with that. You can check that we tested in that NABL lab. So I think that is many of the bacteria, actually almost all bacteria work in similar way. I hope that it should. I think that it should work, because it is not the different whatever is the bacteria we tested.
Okay, because the bacterial wall is supposed to be tougher than other bacilli.
Correct. So because it is also, you can check that we are also lab, we lot of system study we did using the gram positive, gram negative. So we didn't directly check, but the pathogenic bacteria, whatever we check in the NABL laboratory, so that is many of the bacteria is a similar type of properties having.
Yeah, that is checked. It will be very useful, sir, especially in case of sanatoriums where TB wards and all. This will be very useful.
Correct. Yes. Yeah. Any other question? Shubhu.
Yeah, Professor. Actually, you have shown there is some metal nanoparticle or metal surface as well as the silicon. Is it possible that any other like titanium dioxide, other nanoparticles or nano tube basically, do you have successive tested for the this antimicrobial characteristics?
So what your question? Yeah.
My
If you have,
question is, you have already tested that is metal nanoparticles or the metal surfaces, which is basically charged one, kill the bacteria. And you are also tested with the silicon surfaces. Then my question is that whether you have tested with the other like a semiconductor. Suppose I will test it for the germanium nanostructure materials, or we are talking about the like Jedeno. You have talking the Jedeno nanorods and nanostructure materials. So is it possible for everyone, or is it selective nanomaterials?
No.
That is good for this
No,
antimicrobial
right.
substance.
So the things is there is a three mechanism I discuss. One actually the nanoparticle system having can get inside and then that can kill. Another actually the mechanical disruption which is due to the surface feature. So surface feature you can create any of the using any of the material like the PAMAM, so poly MMA, and then also many polymer using silver,
Okay.
gold. And then another function I said, there is a particular type of redox system if you can create like the copper, oxide copper, zinc. So that redox system create the reactive oxygen species. So that the addition to the different mechanical disruption also reactive oxygen species altogether make the faster killing. Now that creating the nano or micro topography, you can use any of the material based on that what you want to use. But ultimately, if you consider that the economically or economically viable process and other things, you have to choose something which is the easily available. And I didn't check any of the metal because I am not working on the metal based things. We just working on the polymer because that is basically we have to almost 8 months, within 8 months of the research, and we completed everything, and then we took the clearance from the authorities and launches the product. So that means I have to choose some polymer which is already exists. There should not be any question from the controlling authority, so that it can go to the faster to the field. So that is the reason actually we use the polymer, and it is the economically viable also. You can see our product actually is much more cheaper than the whatever Juno is selling.
Okay. Thank you very much. Any questions from audience? I think there is no more questions. We thank to Professor Giri. This wonderful talk and mostly informative ones. So that's why I thank to Professor Giri, and I closing this session. Next session will be that Professor Satyajit Sahu from IIT Jodhpur, and his talk is 0D and 2D materials for the various device application. It is good for those are very interested in what is called physics or electronics people. So I request everyone should join and enjoy this talk. Anyway, thank you, Professor Giri. Thank you very much for accepting my request, and thank you very much once again.
Yeah, it is my pleasure. Thank you, Dr. Vibhu, and thank you for inviting me. And then thank you all for your patience and listening to me. And then if you any question, anything, please come back to me. I think that is you have my email ID, everything is there. So I'll be happy to assist or answer any of the questions even after the talk also. Thank you very much once again, and to all, and have a good day. Bye.
Thank you. request Professor Satyajit Sahu to show this PPT for our third session. Professor, can you hear me?
Excuse me.
Hello.
Sir, good afternoon, sir.
Good afternoon.
Good afternoon. Please, it should visible. Your face should be visible. Please.
Is it okay?
Yeah, thank you. Please share your PPT. Before that, I would like to introduce Professor Sahu for his talk entitled 0D and 2D materials for the various device applications. Dr. Sahu obtained his BA MSc in physics from Berhampur University in 2003 and his PhD from Indian Association of Cultivation Science, Kolkata in 2008. Subsequently, he spent 4 years as a postdoctoral fellow in National Institute of Material Science, Japan. He joined IIT Jodhpur as an assistant professor in 2013. Currently, he is working as an associate professor in the Department of Physics at IIT Jodhpur. His research interest lies the area of the molecular electronics, photovoltaic device, organic semiconductors, and 2D materials-based device applications. I request and invite Professor Sahu to give his talk entitled 0D and 2D materials for various device applications. Thank you very much. Now it is over to Professor Sahu.
So shall we start now or we should start at 2 o'clock sharp?
We can start 5 minutes left. So please
Okay.
start. Okay, no problem.
Okay, so thank you, Dr. Swami, for such a nice introduction. So it's
One request is that please increase your voice because this sound is coming a little bit less.
Can you hear me? Can you hear
Yeah,
me?
yeah, now it is okay. Yeah,
Okay, so
thank you.
maybe I should keep it close to my mouth. So it may happen that because the bandwidth issue is there, so in between you may not be able to, get me without a lag. So there might be a lag because I'm having both video and audio going on. So there could be some issues. So please bear with me. Hello.
Yeah, please carry on.
So should I keep my video on?
You close your video. Okay.
Because there might be some issue. So I don't know because at times I face that issue here in our campus. So that's why, most of the time I keep my video off to not having any issue regarding presentation. So let me just.
Okay, Professor, please carry on.
Just a minute, just a minute. I'm
Okay.
starting. Okay, I will share again. So all of you can see my screen, right?
Yeah, it's okay.
Okay. So thank you, Dr. Swami, again. So for such a nice introduction. So good afternoon, everyone. And I'm really thankful to the organizers and especially Dr. Swami for giving me this opportunity to talk to in this program. So it's really an honor to give a talk here in this faculty development program, which is meant for our faculty in various colleges and institutions the around the country. And because it is mainly focusing on the nanostructured material and their applications, so I thought that I should give a presentation which will take these materials into consideration and give a better perspective of how these materials can be useful for us in our daily life and how they can shape the development of humanity in near future, right? So in that regard, I will be talking about the properties and the device application of 0D and 2D materials. Now, so my talk is going to be a very general presentation of nanomaterials, especially two types of nanomaterials. One is 0D quantum dots and the other one is 2D materials. So what are these materials and how are their properties so attractive to us for that applications of these materials which will help us in our endeavor for the development of the society. And in this regard, I will give a little background on the materials, their properties, the synthesis routes, and their applications. Now, in case of 2D materials, I will discuss about the two types of materials. One is graphene, which does not have any band gap, and the other one is transition metal dichalcogenides, which in short called as TMDC. And I call them as the band aid as they provide band gap to the single layer of materials. And in the end, I will discuss about the application of the 2D materials in three devices, and they are photovoltaic device, memory device, and thermoelectric device. So the nanomaterials are a class of materials in which the movement of the electron is confined either in one direction or two direction or three directions. And when we said they are confined, we are referring to a confinement of this charge carrier in a dimension which is less than 100 nanometer. So if we look at the smallest things around us, then there are many things we may imagine which may fall in this category. And in general, if we imagine the dimension of the materials from atoms to the macroscopic scale, then the realm of atom to few thousand atoms or few molecules fall in the category of the nano dimension. Now, though the study of nanomaterials might have started few decades back, but the use of these materials is millennial old. So how do we kind of understand this thing? So one of the oldest artifacts that is known to show the characteristics of nanomaterials is the Lycra cup found in the British Museum. Now, what is the beauty of this cup? This cup shows a dichroism of change in colors with the scattering of light. So when light falls in it, so with the different wavelengths of light, it shows different types of color at different instant of time. So so it is said to be observed because of the presence of the silver and gold nanoparticles that are having different size, and they behave differently to the light. Similarly, another thing one may notice, am I clear?
Yes, please.
Okay. So another kind of thing that we may notice is in the medieval European churches. So there the windows which have this murals and tapestry on the glass, so they also show different colors at different times of the day. So basically the interplay of light with the materials used for these arts, they show us the different colors to us when they get exposed to the sunlight at different times of the day. Now, since the use of nanomaterials on the cups and glass windows through the renaissance of European artistry, humanities have come a long way forward, at which we have now the capability of seeing single atoms and molecules routinely. And this has been possible due to the development of instruments such as the transmission electron microscope, scanning electron microscope, AFM, STM, and so on. Now, one of the major achievements came when researchers observed single atom on materials, and they started playing with these single atom, which is called as atom manipulation. So this atom manipulation they did just to showcase the prowess of their uh, technological development. So basically, first time IBM showed the atom manipulation on a gold surface in which they pulled out single atom from one place to the other place so as to write IBM on the surface of this gold 111 crystal. Now, so now if we look at the application of nanotechnology and nanomaterials in different domains of science, then they are equally important in all the domains of science. And their developments in each of these domains happened in equal measures and helped the domain significantly. For example, if I take physics, then the development of characterization setups such as XRD, AFM, SEM, TEM, and STM, they are some of the names which made the field more versatile to understand the concepts of microscopic scale without any speculation, like unlike what we had in the 1900s or early 1900, we had a lot of speculation that what is going on inside the material, but now it's not at all a speculation, it is not at all a fantasy. We are able to see these things in the microscopic scale, and based on those observation we are making predictions which will take a very short time to come true. Now, similarly, another domain which was benefited immensely is the electronics industry. Now, as the technology that we see around us is due to the manipulation of the atom to its smallest possible scale, and that helped us miniaturize the devices. Now, if you can imagine the situation that we had in the early 1990, at that time we had this bulky mobile phone in our hand and the cost of calls were also very high. But slowly with the development of this electronics industry, because mainly due to the development of nanotechnology, now everybody is having at least one or two mobile phone or rather smartphone in their hand, and this was possible just because of the development of nanotechnology, because the chips get smaller and smaller day by day, and we have now come to a point where we say that we have crossed the threshold that was predicted by Moore, which is called as the Moore's law. Now scientists are tinkering how to go beyond that, right? I'm sure that we will be able to go even beyond that, but at this moment it seems like it has stopped at some point. But we know that as our development in technology progress, we will definitely go beyond even what Morse had predicted in the 1970s and 60s. So now coming back to the first type of material that that I'm going to talk about, which is the quantum dots. And to give you some historical background of this material, so the quantum dots were invented in the 1980s by three set of people, but the first person who reported is Alexei Akimov. And subsequently, Alexander Efros and Louis Bruce at Bell Lab discovered the same quantum dots around the same time. And for their discovery, they have been awarded many significant prizes. Of course, they haven't been awarded the Nobel Prize, but it's not far that these three people will get Nobel Prize very soon. Now, these quantum dots, why are we so interested about these quantum dots? So these quantum dots, if I try to give you some idea about them, then what I can say is that these quantum dots, which are at times called as the 0D materials, as the electron in these materials is confined in all three dimensions, right? So because of this confinement of electron in the quantum dot, so it leads to a very interesting property to the material, which is the discretization of the energy levels. And if you compare the energy levels of quantum dots with the bulk of the same material, then you will see that there is a contrast in the distribution of energy level. In the bulk material, you have continuous distribution of this energy level, which are also called as bands, whereas in quantum dots, they are the discrete energy level. Now, due to the confinement of, due to the confinement, so the energy gap in the quantum dots can be tuned by varying the size of the quantum dot. And as the size of the quantum dot decreases, it is found that the energy gap also increases, right? So when we say that we are confining the electron in the quantum dot, so basically what we are saying is that when we are reaching to a regime where the dimension of the material where the electron is confined is comparable to the de Broglie wavelength of the electron, at that time only we can say that we are at the quantum confinement level. And if it is not in that particular regime, then we will not be able to see the effects of quantum confinement. Now, one of the important concepts that we must understand regarding quantum dots is that their electronic properties will be defined by the distribution of the density of states. Now, density of states is a concept which is highly essential to understand because it tells us that how many energy levels are available for the particles, for the electrons to be distributed on a particular energy band, right? So, so as we see here that the density of state for a bulk is varying continuously with respect to energy. But as the size keeps decreasing, the confinement effect starts to show up. And for the 0D material, as you can see that the density of states varies as a delta function, which resembles with the discrete energy level of atom. So basically what is happening is that the density of states of the quantum dots is going close to that of the energy level distribution that you find in atoms, right? So now if we look at
the properties of now if we look at the properties of the quantum dots, then their optical properties mystify people, as the way they behave is completely different than anything we have seen. For example, the quantum dots absorb and emit at different wavelengths when excited with blue light depending on their size. Hello?
Emit on their size.
Hello? I'm getting an echo. Hello? Yeah,
So please carry on. I will mute this person.
okay, thank you. Right. So now, for example, the quantum dots they can absorb and emit lights of different wavelengths depending on the size of. Is somebody asking something? I mean, there is a breaking voice I'm getting, but it's not very clear.
Sachidanand Pathak, why you make noise?
Is
Okay,
there any
please.
question from his side which he wants to ask or something?
No questions. Question will ask in last time. Last of the.
Okay, thank you. So now the energy of excitation and emission depends on few things such as the band gap of the material, the exciton binding energy of the material, and the confinement energy. These are the three things which determine that at what wavelength your absorption and emission will occur in the quantum dot. And because of this, the optical properties of the quantum dots can be tuned according to our wish. Now, if we would like to talk about the electrical properties of the quantum dots, then in terms of its electrical properties, we can have some serious control over their properties, like the way we did say that the optical properties can be tuned, the electrical properties can also be tuned. Now, electron hole pair generation occurs to the absorption of energy, and the transition of electron from conduction band to valence band will release photon. And in if we take a fluorescent system, then in fluorescent system only one excitation is generated, or only one exciton is generated. But in quantum dots you can generate multiple exciton because of its properties. So if we take the quantum dots to study their electrical properties, then we can have two types of quantum dot. One is called as the type 1 quantum dot, where you have a core cell like structure where the core has a smaller band gap and the cell has a larger energy gap. So because of this kind of arrangement, what happens is that when you are shining light, the electron hole pair will be confined to the core only, right? And because of this, you get to see a high photoluminescence in the system. And unlike the type 1 quantum dots, we have type 2 quantum dots where the core material has a higher energy gap and the shell material has a lower energy gap, and they will be distributed in such a way that when you are shining light, the electron and hole will be created in the two different layers. That is, the electron might be created in the cell layer and hole might be created in the hole layer, in the core layer. And because of this, you will see that there will be a wider wavelength of emission, right? So that's how, if we can play with this core and cell layers, we can achieve our desired output from the quantum dots, whether we want high photoluminescence from the material, or we want wider luminescence from the material. Depending on that, we can play with these two conditions and we can achieve our desired requirement. Now, when it comes to the synthesis of the quantum dots, so we have seen many methods available in literature for the synthesis of quantum dot based on the physical, chemical, and biochemical methods. But all these synthesis routes can be classified broadly into two categories, and that is the top-down approach and the bottom-up approach. In either of these approaches, there are some pros and cons. For example, in the top-down approach, we see that the quality of the quantum dots is poor and the quantity is less. You also see a polydispersity along with high amount of contamination in the quantum dots. Now, if you take the bottom-up approach, what you will see is that in this approach, the quality of quantum dots is high, and there is a monodispersity of the quantum dot. Also, is a uniform size distribution. But the con in this method is that you get to obtain a small quantity of this material, and this method is also expensive. So now some of the popular top-down and bottom-up methods I have listed down here, and they are widely used depending on the availability of the resource of that researcher. But more or less, you can find that one of the methods will be used for the synthesis of quantum dots. But one of the popular ways of synthesis of high quality quantum dot is by the use of hot injection based colloidal synthesis. So this is a very um, important synthesis route for me because I use this synthesis route day in day out in my lab for getting high quality quantum dots of whatever type of quantum dots I look forward to. And in this method, a precursor for the synthesis of the quantum dots was prepared in inert condition and in vacuum at high temperature. So because of the availability of high temperature, you see that the crystallinity of the material is very good, and you will see that there is a monodispersity of the quantum dots that is prepared because of the way they are prepared in this method. So here, as I said, that in this method also you get a very small amount of quantum dots, and but the amount of quantum dot that I get in my lab, that is sufficient for the kind of device application that I am interested in. So, but if you want to synthesize them in large scale, then perhaps it is better off using some other method than using the this colloidal synthesis method. So that if it is for, let's say, for fabricating big devices, then in that case you may not see that this kind of method is that widely popular. But for large scale R&D scale device fabrication, this kind of synthesis route is very widely used. Now, the next thing that we will talk about is the 2D material. And before that, so the 2D materials development from the beginning of the discovery of graphene, I must tell you something about their development over the years so that you get a perspective of how they have come into fore uh, as the research progressed with time. So the growth and development of 2D material started with the discovery of graphene in 2004 by a group from UK, and the very exciting properties of graphene, especially its electrical properties, made the whole world go crazy behind it. So we know that what kind of research that went through after the discovery of graphene. Everybody was just going behind using graphene in their research. So around the same time, an insulating material called boron nitride was also discovered, right? So the usage of graphene was restricted due to the metallic behavior and also the absence of band gap. Because of these two things, the graphene was useful only in particular applications. So this motivated many researchers to find out is semiconducting 2D materials. And in 2005, a host of semiconducting 2D materials such as MOS2, WS2, etc. were discovered. And after that, the development of 2D materials took a leap off. And since then, new types of 2D materials such as silicene, germanium, and phosphine came into existence. Now, lately, new 2D materials of various interesting semiconducting magnetic materials have started coming into picture because of the development of new growth technology, which are facile and easy to control. And these include zinc oxide, V2O4, gallium oxide, etc. So these are the new type of 2D materials that you would see in the literature, and they are discovered very recently. So many new properties of these materials are yet to be discovered. So slowly they are finding new application of these materials as well. So let's talk about graphene a little bit in detail. So as I said that the first type of 2D material of our interest is graphene, and which was discovered by these two gentlemen, Andrei Gaim and Konstantin Novoselov. So because of which they were awarded the Nobel Prize. And they took a very simple method to get this material. So they took just a lump of graphite and used a scotch tape to mechanically exfoliate the graphene from it. So, and since then the scotch tape exfoliation method has been legendary because everybody is using to exfoliate other type of materials like the way they did for graphene from graphite. Now, what are these graphene? So these are a single layer of carbon atoms arranged in a 2D hexagonal honeycomb lattice structure. And here each carbon atom is connected to 3 neighboring carbon atoms with a sigma bond, and the fourth bond is a pi bond formed out of the plane of the graphene sheet. And due to this, a conjugated structure is formed which helps in delocalization of the electron. And because of this delocalization of electron, you will see that the conductivity of graphene is high. So basically you have a single bond, double bond, alternate single bond, double bond arrangement that is observed in graphene, which helps it achieve a very high conductivity in the system. I'm sorry. Now, if we talk about the electrical properties of graphene, then it is a material which has no band gap, as I have already mentioned, and the conduction and valence band meet each other at the Dirac point, right? Now, due to this, some very interesting properties are noticed in graphene, which are the anomalous quantum Hall effect, the ambipolar electron and hole transport in the system, then half integer quantum Hall effect, and the observation of Casimir effect. These are all exotic phenomena which are observed in graphene, and these are all into the realms of quantum mechanics, right? So when quantum mechanics dominate over classical mechanics, you observe these kind of behavior, which we see in graphene. Now, some other interesting properties of graphene can be categorized into optical, magnetic, as well as some other material which are some other properties which can be categorized into the mechanical strength of the graphene. So some of these properties, if I want to cite, then they include that the high opacity of the material, presence of nonlinear Kerr effect, and the magnetic quantum Hall effect are some of the very important exotic phenomena that you will see in graphene. Now, if we talk about the different forms of graphene, then the graphene can be found in various forms, such as the monolayer and bilayer or multilayered sheets of graphene. Then you get the turbostatic sheet, which is another important form of graphene, which has recently come up. And the graphene nanoribbon, graphene quantum dot, graphene oxide, sorry, and 3D graphene are some of the other interesting forms of graphene that have come up in the recent time. And their applications are slowly realized in our real world situation. So we may see many such applications coming forward in our future as well. Now, some of the important methods for synthesis of graphene are categorized into the mechanical, chemical, and splitting methods of the synthesis of graphene. Also, there is this chemical vapor deposition method, which is widely used for a large area production of graphene. And this mechanical exfoliation method of the synthesis of graphene is very legendary because this is the way the first time graphene was discovered. And the chemical vapor deposition method is very widely used for synthesizing large area synthesis of graphene. And this all these methods what I have mentioned here, so they depend like what method a particular research group will follow will depend on the availability of resources again. Now, in terms of the application of graphene, so their usage is limited due to the constraint of not having a band gap, which allows them only to be utilized as an electrode material for devices. Right. So I have already mentioned that they do not have band gap, and this restrict their usage because it's like the metals which do not have band gap, and their behavior is more like metal. That's why they are a very good option for electrode material. But having said that, some researchers have used graphene for device application, not only restricting themselves for electrode uses only, but they have used graphene the device to get some sort of heterostructure, right? And here I have shown an example of a, device application, and this device application is the solar cell application. So here, due to the presence of graphene, they have found that the carrier recombination at the interface has been suppressed. And because carrier recombination leads to decrease in the efficiency of the solar cell, so if you can reduce the carrier recombination by some mean, then it will definitely lead to a highly efficient solar cell. And that's what they have shown here, that whenever they introduce graphene in their system, it basically provided a heterostructure. And because of that, the recombination process at the interface was suppressed, and due to which they got a better efficiency from their device. Now, the host of 2D materials which are developed from the last so many years can be categorized as conductor, semiconductor, and insulator. And the response of the materials to the electromagnetic radiation spans from low energy microwave to high energy UV region, right? And most of the time for device application, we are interested in materials whose response falls in the visible or near IR region, right? So the band gap of the material that we will be looking for can span from zero point 0.5 to 3.2 electron volt. And for us, mostly we are interested in the materials that fall in the visible region, because for our application in our lab, we will be looking forward to use them for optoelectronic application, and especially in the visible region. So the exciting properties of this 2D material can be seen from this particular slide. So we can see that the 2D materials, they have a unique behavior, and it's not only restricted to semiconductors, but has a large spread into other domains as well. So in the mechanical front, they are ultra thin and have high Young's modulus and have very high strength. And as far as optical properties are concerned, they have tunable band gap and high transparency. And for the unique electrical properties, they have high mobility, as good as graphene, and can be tuned as semi-metallic and semi-conducting properties. Now, due to the high absorption coefficient, they are very good candidate for optoelectronic application. And lately, their magnetic properties are also explored in new 2D materials, and they showed ordered magnetic behavior. So these are some of the unique properties of 2D materials, but they are not restricted to these only. There are some new materials which are coming up and which are categorized in the 2D materials, and they their properties are even exotic than what just now I mentioned for the 2D materials. Now, because I have been talking about this 2D materials, which is called as the transition metal dichalcogenides. So what basically are these transition metal dichalcogenides? Now, as the name suggests, they are consisting of the transition metals, and as shown in this blue box in the periodic table, and the chalcogenides here are shown by the red box. Now a combination of these two materials gives us this TMDC on the transition metal dichalcogenides. Now this TMDC can be synthesized in mainly three different ways, which are again the exfoliation method, the chemical vapor deposition method, and the molecular beam epitaxy method. And the exfoliation can occur in mechanical or chemical or destructive thinning way. So the most common large area synthesis method is the chemical vapor deposition method. While you use the molecular beam epitaxy method to provide high quality defect free synthesis of TMDC, which can be controlled in the atomic layer. I mean, you can grow single atomic layer of these materials by using molecular beam epitaxy. But the problem is that this is a very high expensive way of synthesis of TMDC. So that's why the most widely used method of synthesis of TMDC is either the exfoliation method or the chemical vapor deposition method. But then with the exfoliation method, you must have the crystal with you from which you exfoliate mechanically or any of the methods just now I mentioned. But chemical vapor deposition also gives you some amount of control, not as good as that of the molecular beam epitaxy, but it is still fine. People get very good quality TMDC by using chemical vapor deposition methods. Now, in terms of application, I will be discussing three of its device applications, such as solar cell, memory device, and thermoelectric device. And out of which the thermoelectric devices I will explain in depth, as the presentation will showcase the work we are doing in my research group. Now, coming back to the solar cell. So a solar cell is a device which is operated under sunlight and uses it to create electron hole pairs. And these electron hole pairs, they will get dissociated at the interface of the p and n type material that you use for the fabrication of the device. And after the separation of this electron hole pair, they'll move towards the respective electrode, and thus they give a current in the circuit. So basically a solar cell acts as a normal diode in dark, but as soon as light shines on it, they will act as a current source. And if you look at the IV curve, then you see that here I have shown the IV curve in dark and in light. So in dark, the IV curve looks like a normal diode characteristic curve, but in light, you see that the IV curve has come down, and mostly in the fourth quadrant of the IV characteristic curve, you see all the observation related to solar cell will be found. Now, if you look at the fourth quadrant, the area under the curve is very important in this quadrant, as it defines the efficiency of the solar cell through a term called as fill factor, right? So that's why we must be very careful that what is the area that we are getting. Higher the area of this region, better is the efficiency of the solar cell. Now, as I have already mentioned, that the properties of TMDC that enables it to be used for solar cell applications are its band gap, which lies in the region that gives maximum efficiency, and the high absorption coefficient of the material allows it to absorb more amount of light that is falling on it. Now, though it has these two properties that can, in principle, allow it to be utilized in solar cell, but the absorption of light in these materials is only of the order of 10%. And why is it happening? Because it has a very high reflectivity as well. The surface of the material has high reflectivity, because of which only a little of the light gets absorbed by the material, and the rest of them will be reflected from the surface. So to enhance the light trapping in the device, various other methods are used. For example, they use resonators along with the TMDC to capture more amount of light, so that that light can be utilized um, for the formation of the electron hole pair. And also they use some sort of spacer group along with the TMDC to enhance the light trapping properties in the devices. So not only the use of TMDCs can give you a high efficient solar cell application, you must maneuver some other techniques and tools along with the TMDC in your device, so that you can achieve high efficiency from your device. So now TMDC can be used in multiple ways in the solar cell, and here I have showed the four broad ways in which it can be utilized. So they are as counter electrodes, or can be as active layer, or as whole and electron transport layer. Now again, each of these categories are grouped into various other ways of application also, like the way it is shown in this schematic, that each of these category is having multiple options again. So depend kind of depending on what kind of research has gone into it, so this category has come up. Now, if I choose few examples from each of the category, now here you can see that I have shown that how TMDC can be used as counter electrodes to realize the power of TMDC towards device application, and specifically towards the high efficiency solar cell. So here you can see that MOS2, one of the 2D materials, one of the TMDCs, so the nanoparticles of MOS2 is utilized as one of the counter electrode in DSSC, that is dye sensitized solar cell. And because of the use of MOS2 nanoparticle, the efficiency of the devices has increased significantly. And even beyond that, what they did is that they included the MOS2 material along with a molybdenum oxide. And what they found is that when they fabricated devices out of this combination, the efficiency that they achieved were comparable to that of the efficiency of DSSC, where usually the standard counter electrode that you use is the platinum counter electrode. So it is comparable to that. So what they observed is that by using the MOS2 in a clever way, you can basically play around with the efficiency of solar cell. Now similarly, TMDC as an active layer in the device can also be seen to be used by various research groups. So here I have seen that the device has a heterojunction, and in this heterojunction, one of the layers, one of the active layers of this device is your MOS2 layer. Now this MOS2 layer here, it is acting as an N-type layer, and there is a P-type silicon layer along with MOS2, and from this device they got some efficiency, but then the efficiency is not that high. But when they use the same device but with a little tweak, that means in between the MOS2 layer and the silicon layer, they introduced a insulator, which is the silicon dioxide layer. It's, of course, the thickness of this insulating layer is very small. So when they introduced that, they found that the efficiency of the device has increased significantly, and this they explained that this kind of increase in the efficiency is due to the suppression of the charge recombination at the interface of these two type of material, and because of this the device efficiency has gone up. Now the next application is the memory switching application. So what is this memory device that I'm talking about? So basically these are devices which show two different level of conductivity at the same voltage. Now how is it possible? So what happens is that when you do the IV scan of this device, you will see that it follows in two different paths for conduction. Now the low conducting state is called as the off state, and the high conducting state is called as the on state. So this kind of behavior can be translated to the on and off states of transistor, and because we know that transistors are used for used as switching devices, so we can correlate our phenomenon to a switching device. That's why we are calling this kind of behavior to be falling under the category of switching device. Now, the difference between this device and the transistor based device is that here the states are due to the change in the resistance of the device. Hence, we call them as resistive switching device. So nowadays you may be coming across this term called RAM, which is resistive random access memory. So they are nothing but the resistive memory devices, right? Now, primarily the switching in the devices is due to one of the 6 possible reasons, as I have shown here. So you can uh, categorize the switching behavior obtained in your device in one of these 6 switching behaviors. And some of the main reasons why you observe the switching phenomenon in the devices are like filamentary filamentary conduction of the ions which are coming out from the electrodes, then the oxidation and reduction of the active materials, or the space charge accumulation in the devices. These are some of the important reasons which will be utilized frequently for explaining the behavior of memory devices for a particular kind of observation. Now, TMDCs have played a significant role in the switching device application as well. And for example, in WS2 based devices, they have fabricated these devices, and they show that the switching behavior in their devices is occurred at a very low power, like you give very low energy to your device to operate, which is very important because now you have so many transistors in your processors in any of the computing devices. Now these transistors, they draw a lot of power. Now if they draw a lot of power, so a lot of power is also wasted in the form of heat, right? So to control that, what they are thinking is that to use transistors which will use very little power. So if you can do that, the losses will be accordingly, or the proportionately will be there, and which will be even smaller than what it used to be. So that's why low consuming power switching devices are the need of this hour. And they also observed low leakage current from their devices, and because of this low leakage current, they have low dark current, which eventually leads to high on-off ratio, because you want to get your on state and off state confidently without any doubt. So to do that, you must have a very distinct on and off state of very high magnitude or by very high order of current for each of these states, so that you can distinctly say that you are operating your device for the on state or the off state. And it has been observed that the device also has the ability to store multiple bits at the same voltage, and this kind of behavior helps in high density data storage device application. And moreover, the advent of memory stores, a class of memory devices, led to the use of TMDC even further, as they can provide a large surface area for operation and can store and process the memory at the same place, which is how our brain operates. So because of that, a lot of interest has been grown in the TMDC based memory device research. So this kind of realization leads to the neuromorphic application of the material, right? Now, the next class of device application that I will be talking about is the thermoelectric devices. And if we would like to use the TMDC for thermoelectric application, then we must know what is thermoelectric effect. So there are three types of thermoelectric effect, which are the Seebeck effect, the Peltier effect, and the Thomson effect, and we are interested in the Seebeck effect. So this is a phenomenon where we are basically getting a potential across a semiconductor by maintaining a temperature difference across the semiconductor. And because of the temperature difference, this drives the charge carriers to move in a way that gives rise to current in the circuit. And here, as you can see, I have shown an animation how this Seebeck effect comes into picture. So now let us see the Seebeck effect in TMDC, the kind of TMDC that we use in our study. So how we observe TMDC. So let me tell you that this observation that we have, this is purely based on the theoretical calculation. But recently we have started some experiment to explore the possibility of matching theoretical outcomes from our devices in reality. So hopefully we will be achieved to show the same kind of behavior that we observed theoretically in our experimental devices as well. But the kind of presentation that I am going to show from this slide onwards, they are basically based on the theoretical calculation we did in our group. So the first effect that we would like to see is the effect of mechanical strain on the thermoelectric behavior of monolayer of WS2. So here WS2 is a TMDC which has a hexagonal honeycomb-like crystal structure, crystal lattice, and the lattice constant for the crystal is 3.19 angstrom. And for studying the properties of WS2, we basically used density functional theory using the PB GGA exchange functional in the projected augmented wave potential. And to study the thermoelectric properties of the material, we use the Bolt-Trap package using constant scattering time approximation. And here we introduce strain to the material during the calculation of the thermoelectric properties. And these strains are both axial and both biaxial and uniaxial compressive and tensile strain. So what we did is that we introduced a strain up to 6% for both biaxial and uniaxial strain. And in both the cases, the lattice parameters changed by some percentage as we kept on increasing the strain in our system. So now the different material properties of WS2 with respect to the chemical potential with variation in the temperature was studied, and these studies are targeting to the band gap region only, because the observation that you see in the thermoelectric devices are can be inferred by looking at the band gap region. So these studies are that's why we are targeting the band gap region. Now the carrier concentration variation with temperature, as you can see, it suggests that the carrier density is 0 in this region at room temperature, but as you increase the temperature it is changing. But for the Seebeck coefficient, it is opposite, as the value if high at room temperature, but it decreases with increase in temperature. So similarly, for the conductivity of the material, it increases with increase in temperature in the band gap region. So these three things can be observed with the change in temperature for the WS2 monolayer that we have used. Now the other parameters that we studied with the application of temperature is the power factor, because power factor is something which tells us how efficient our thermoelectric device. And it is found that the power factor increases with increase in temperature in both the p-doped as well as n-doped materials, right? So the region above the Fermi level is the conduction band region, and the region below this is the valence band region. So the BBM and CBM here I have shown them, and I have shown the dotted line to demarcate these two things. So now the density of states of these materials follows the trend of power factor what we observe, and that is there are three peaks in the conduction band maxima in the conduction band, and only one peak on the valence band side, right? So the conductivity increases with increase in temperature, which suggests that the material is a semiconducting material. So now the study of Seebeck coefficient, power factor, and the band gap with applied biaxial strain and temperature tells us what is happening with strain. So the Seebeck coefficient is higher at room temperature, and it first increases and then decreases with the biaxial compressive strain, but it decreases with biaxial tensile strain. But for the power factor, it is higher for the material at high temperature, right? So it first increases and then decreases with increase in the biaxial compressive strain or biaxial tensile strain, right? But for the Seebeck coefficient and band gap, it first increases and then decreases with biaxial compressive strain, but it decreases with biaxial tensile strain. Similarly, the effect of uniaxial strain at different temperature also was studied, and we found that the Seebeck coefficient is higher at room temperature, and with applied uniaxial compressive strain, it first increases, then it starts decreasing except at 300 Kelvin, which is at room temperature. But with the uniaxial tensile strain, it starts decreasing. Okay, so for the power factor is higher at high temperature, and it first increases and then decreases with applied uniaxial compressive strain, except for p-doped material. So the band gap of the material also increases and then decreases with the uniaxial compressive strain, but it decreases with uniaxial tensile strain. Now we wanted to know how the strain affects the band picture of the material. So what we saw is that for the unstrained material, the band gap is a direct band gap, and the electron valleys are located at the high symmetric point, as well as at a point in between two high symmetric points. right? Whereas for the valence band, almost whole valley degeneracy was observed. Okay. Now, when we applied 1% biaxial compressive strain, so we found that the electron valleys are also degenerating, whereas the whole valley degeneracy is broken. So initially we had whole valley degeneracy, but as we applied the 1% BCS, then the whole valley degeneracy is broken, but you see electron valley degeneracy in the system. Similar observation was also made when the strain was uniaxial, but with 2% uniaxial compressive strain, right? Now, with the application of tensile strain, it was found that with both the biaxial tensile strain or uniaxial tensile strain, the whole valley degeneracy remains intact, and there is no observation of electron valley degeneracy in the system. And when we increased the percentage of tensile and compressive strain on the WS2, it was found that the electron as well as the whole valley degeneracy were broken, and the band gap was transformed from direct band gap to indirect band gap material. So these are the observations that we got in the band picture, and this band picture clearly suggests what is happening to the thermoelectric properties of the materials. And now to explore the reason of enhancement of the thermoelectric parameters, we tried to probe the band picture of WS2, and we found that the valley degeneracy is the reason behind the thermoelectric behavior that we are observing, and the effect is prominent at lower strain. That's what we saw. And the degeneracy causes the conduction band carriers to have multiple channels to do the transition between the valence band and the conduction band, right? And the application of the biaxial compressive strain or uniaxial compressive strain favors the electron conduction, but when you are applying biaxial tensile strain or uniaxial tensile strain, it favors the whole conduction, right? So with higher degree of strain, the degeneracy is broken, and thus the thermoelectric parameters also degrade. So basically, the reason behind the observation in our system can be attributed to the visibility of degeneracy in the valley degeneracy in the conduction band and in the valence band. So now we wanted to find out why in the first place degeneracy occurs with the application of strain. And for that we studied the band decomposed charge density of the valence band and the conduction band at high symmetry point. And the valence band at gamma point is mainly dominated by the GZ2 orbital of the tungsten atom and PZ orbital of sulfur atom. And whereas the valence band at K point is contributed mainly by two degenerate states, and that is the tungsten atoms dx2y2 and dxy orbitals, and there is negligible contribution of sulfur atom at these points, right? Similarly, the conduction band at K point is mainly dominated by the tungsten atoms dx2y2 and dxy orbital, and there is very little contribution from sulfur atoms at these points. But the conduction band at delta point has contribution from both tungsten and sulfur atom. So when strain is applied, the bands at K point remain relatively unchanged, as bands at K point are mainly dominated by the tungsten atom, which is sandwiched between two outer sulfur atom planes, hence less sensitive to strain, and the strain is mostly applied to the outer layers, right? So this is how degeneracy in our system appear due to all these the contribution of the orbitals of the tungsten in the sulfur atom. Now next we try to study the effect of spin orbit coupling to the thermoelectric performance of the TMDC, and this time the TMDC that we used is HFX2, and here X is basically replaced by sulfur or selenium or sulfur and selenium, right? When we take both sulfur and selenium along with HF, we call that as a Janus monolayer. And the crystal structure of the material is similar to that of the cadmium iodide crystal, and the lattice constant of HFS2 and HFSC2 were kept at 3.65 and 3.78 angstrom, and for the Janus monolayer the lattice constant was kept at 3.71 angstrom, right? So the different bond angles can be found out from the literature because they are very easily available, and here in this slide I have shown the different bond angles as well. Now the study of the thermal stability of the material is important because it gives the information whether the material can remain stable at higher temperature or not, and this calculation was performed using a PhonoPy package along with DFT, and our study showed that the material is thermally stable as there is no mode in the negative frequency, right? And there are 3 acoustic modes and 6 optical modes in the vibrational picture, and for the Janus monolayer of HFSE2 the optical and acoustic branches overlap, which suggests that the scattering of phonon is occurring, and which is not seen in HFS2. So in HFSSE you see the scattering of phonon occurring. Now once we confirm the thermal stability of the material, we try to probe the band structure of the material with and without considering the spin orbit coupling, and we found that the band gap is indirect in nature when we are not considering the spin orbit coupling, and the band gaps are like 1.3, 0.65 and 0.834 electron volt for HFS2, HFSE2 and HFSSE Janus monolayer, right? But when we introduced the spin orbit coupling, it is found that valence band spin splitting occurs, right, which is higher for HFSE2, right? And the band gap of HFSE2 and HFSSE decrease slightly due to the spin orbit coupling, right? So then we tried to relate these observations with the density of states of the material, and the projected density of states suggests that the HFS2 and HFSE2 valence band is contributed by the px and py orbital of the sulfur and selenium atom. Similarly, for the Janus monolayer, the BBM is contributed by the px py of px py orbital of selenium and py px orbital of sulfur atoms, but more contribution comes from the selenium atom. And similarly, for the conduction band minima, the dz2 dzx dxy of hafnium atom and pz and sulfur and pz of sulfur and selenium atom, they contribute. So the projected density of state picture also gives us the information about the band gap of the materials accurately when we consider the spin orbit coupling interaction. Now with spin orbit coupling in our hand, we try to find out the thermoelectric parameters of the material, and the Seebeck coefficient is highest for HFS2 for n-doped material, and it decreases with increase in temperature, and also the power factor increases with temperature, and it is highest for n-doped HFS2. And these observations are obtained when you have the spin orbit coupling contribution was not counted, right? Now since HF is very heavy, so we must consider the spin orbit coupling. That's what we tried to first find out the changes in the band picture, And now with the spin orbit coupling, we try to find out what is happening with the thermoelectric parameter. So when we included the spin orbit coupling into the calculation, we found that the Seebeck coefficient does not change much, but the relaxation time, which is scaled to the conductivity, it is increasing with the inclusion of spin orbit coupling. And due to this, the power factor increases, and it is found that the effect is higher for the n-doped material, right? Then we shifted our focus to the band picture of the material, and it is observed that without SOC, the CBM or the conduction band minima does not have any band splitting, whereas the valence band has dual band splitting. But when we introduced SOC, that is the spin orbit coupling, we found that the conduction band splits into two, but the splitting in the valence band remains same, right? So thus there are some degeneracy in the bands which increases with the power factor of the n-doped material when we introduced spin orbit coupling into the system. Now the thermal conductivity of the material with temperature shows a decreasing pattern, and the thermal conductivity is higher for HFS2 and lower for HFSE2, and the study of the group velocity of the phonon with frequency also reiterates our observation that there is no gap between the acoustic and the optical branches in HFSE2 and HFSSE. So this is because the group velocity is higher for HFS2 and lowest for HFSSE. And we also found that the phonon lifetime is also following the same trend, right? So these effects lead to increase in the phonon scattering in HFSE2 and HFSSE. So now the quality of the thermoelectric behavior is quantified by using the Jetty factor, and Jetty factor will be higher for the material for which the electronic and phonal thermal conductivities are low, because as you can see here, we have the conductivity due to the electron and the phonon. They are in the denominator of this expression for Jetty factor. So lower these thermal conductivity for both of these contributions, higher will be your Jetty factor, which defines the efficiency of the thermoelectric device. Now it was observed that Jetty increases due to the spin orbit coupling, and this is because we have seen that with the introduction of spin orbit coupling, valley degeneracy comes into picture, and which increases the power factor, right? And it was also observed that the Jetty is higher for the n-doped HFX2, which means HFS2 or SE2, and since the material showed very good Jetty at room temperature, so thus we can use HFX2 as room temperature thermoelectric application, because most of the thermoelectric devices, you see their properties at relatively higher temperature. So next we shifted our attention from TMDC to some other 2D materials such as XI2, where X is SN or SI, and the monolayer has a hexagonal honeycomb like structure again, and the lattice constant for these two types of crystals are 4.5 to 4.1 angstrom, and phonon dispersion studies tells us that the material is thermally stable as there is no mode in the negative frequency region. Also, there is finite gap between the two branches for SNI2, but there is no gap between the two modes in SiI2. So we can expect scattering of phonons due to this overlapping in SiI2. Now both SNI2 and SiI2 have indirect band gap, and the value of these band gaps are like 2.06 and 1.63 electron volt for SNI2 and SiI2 respectively. And a close look at the density of states picture of this material tells that the VBM of these materials has degenerate states, and the contribution to the VBM comes from Px, Py and Pz orbital of the iodine and S orbital of Sn or Si atom. whereas the contribution to CBM comes from Px, Py and Pz orbital of Sn or Si atoms. And we also observe the optical properties such as the absorption spectra, the dielectric constant, etc. And we found that using time dependent density functional theory, these observations, they match with the reported optical properties of this material, and it was found that these materials have high absorption coefficient, which is essential for using them for any optoelectronic application. Now the thermoelectric parameters of this material with temperature was found out, and it is seen that the Seebeck coefficient is highest at room temperature and decreases with increase in temperature, and the power factor also increases with temperature, and the electrical conductivity also increases with temperature. These values are higher for the p-doped material in comparison to the n-doped material. And regarding the thermal conductivity of the material, we studied using the linear dispersion Boltzmann transport equation, and using this it is found that the thermal conductivity due to lattice here it decreases with increase in temperature, and the phonon group velocity and phonon lifetime are also less with increasing frequency, and the frequency response also validates our phonon dispersion study of overlapping of the optical and acoustical branches for these materials, and this causes the scattering of phonons, and thus it decreases with it decreases the lattice thermal conductivity. Now, as I have already said that the quality of thermoelectric material is quantified by the J factor, which is higher if the thermal conductivity is low and the power factor is higher. So when this condition is satisfied, we can expect that the J factor will increase. So the J here is more for the p-doped material than that of the n-doped material, and since the J is substantial to be utilized at room temperature, we can say that this material is good for room temperature thermoelectric application, right? And so these are some of the studies that we did in our research group regarding the thermoelectric application of the different types of TMDCs. We are still doing some more theoretical study on some new materials, new TMDCs, and as I said that we are also exploring the possibilities of correlating these theoretical data with the experimental data. So we have started doing some experiments, and hopefully we'll be able to match with our theoretical data. And finally, I'm thankful to my students who have contributed to these works, especially Jayanta and Atanu, whose hard work gave rise to this nice work just now I discussed. And also I'm thankful to my MSc students who worked with me for their thesis and project. Thank you for your.
Thank you very much, Professor. So,
yeah, did it take a lot of time?
the cup of coffee is not available in it is only virtually, so everybody will enjoy
Yeah,
to just to see.
that's why I have asked for a virtual coffee.
Okay, and now it is open for question session for the participants. Please ask questions to Professor Satyajit Sao. So, please, any questions from audience? Any question? Okay, so I have this very means just a query for this thing. So you are making 2D material by means of which method?
You mean to say synthesis you are talking about?
Yeah, synthesis.
So here at this moment, I have bought some crystals of 2D material, for example, MOS2 and WS2. So at this moment, we are exfoliating the monolayers
How?
and mechanically, like using Scotch tape method.
Okay, okay,
So
okay.
you exfoliate them and then transfer the substance and then
Did you try for this what is called chemical route things?
CVD method, since I do not have a CVD in my group, though it is there in our institute, I'm trying to collaborate with few of my colleagues to get access to this CVD instrument. So if I get access to their instrument, then I'm planning to use their system. However, I am planning to, in fact, I have already submitted couple of proposals wherein I have asked for a plasma enhanced CBD system for the growth of these TMDCs in my own lab. So let's hope that these projects gets through so that I can get my own CBD system. Of course, there is a limitation in terms of getting these TMDCs using mechanical exfoliation method, because it is first of all a very time consuming process in getting the monolayer of these materials, and second of all, these crystals are itself very expensive. So at this moment I am using this exfoliation method, but yeah, in future I would like to extend it to the chemical routes, which will give me a lot of control over the growth of these materials.
Okay.
Yeah.
So actually, thing is that Professor, you have shown the switching applications.
Mhm.
So what is the on-off ratio? You are
On-off-
writing it is very high, but what
Yeah,
is the
so
quantitative of these things?
on-off ratio with the WS2 based switching device is
Mhm.
reported to be 10 to the power 6, which is very
Oh,
high.
then good, good, good.
Yeah, so it's very high. So that's why this DMDCs are of a lot of demand for using them for this neuromorphic application, right? So because these switching devices are one of the ways that you can use them for neuromorphic device application. So and because they give a
What
large
is the
area. Yeah.
voltage you have applied?
The voltage is very small, like around like 0.4, 0.5 volt. You see that there is a current of 10 to the power minus 5 ampere. So that is the
Okay.
on-state current, and the off-state current is like 10 to the power minus 10 or so. So because of this large difference, and it occurs at very low voltage, that's why the power is still pretty low.
Actually, if because it is a 2D material,
Hmm.
so I expect because there is the electric field is very high.
Mhm.
Because it is, if you think that what is the dimension of the channel? So your
So
measurement.
you can use this material either by taking a composite with some other material, or you can use a lateral structure device for the study. Now, the one that I am talking about, in that what they did is that they use this TMDC along with a polymer. Like, so that polymer acts as a matrix, and now this layer is sandwiched between the top and bottom contact. Right.
Okay.
So in that case, they found this this on-off ratio. But if you go for lateral device structure, then in that case you have control over the channel length. For the device that I am talking about, there the width of this active layer is of the order of, let's say, 150 to 180 nanometer, not more than that.
So another very means I'm very curious about this thing. You are talking about the changing of strain from tensile or compressive in
Yeah.
to the thing that what is the strain order? Order of strain.
Okay, so
Current.
I have given this strain in terms of percentage. Let's say you
Okay.
have an unstrained material and you slowly increase this strain in terms of some percentage, like 1%, 2%, and like this way I've gone till 6%. Now, because this study is purely on a theoretical basis, so I cannot at this moment tell you that
Okay.
actually how much strain you can apply. but given the mechanical strength of this material, you can apply a very high strain to your system. So I have seen some literature where they talk about a strain of the order of some gigapascal or something. I don't know whether that much is possible or not, but then there somewhere I have seen this figure. But when you are doing a theoretical calculation at that time, you just adjust it in a way that you are increasing the strain in terms of percentage rather than giving some actual physical value to this strain. So when you do experimentally at that time, perhaps you have to measure it experimentally, but theoretically you can just do it, do away by just applying percentage wise strain.
Do you control the mobility? What is the mobility here?
Mobility.
Because due to strain?
Mobility due to strain, I have not calculated, but that will be an interesting study if we study the mobility of these materials under strain. But because we are mostly focusing on the thermal conductivity, because we want our devices to be operational for thermoelectric application. So mobility is at this moment we didn't think of calculating it because it is not contributing as such towards the thermal conductivity.
Okay,
So
thank you.
that's why we did not do that.
Okay, thank you very much. Any questions from audience, please? I think there is no more questions, so I rest the session here. And thank to our speaker, Professor Satyajit Sahu, and ended this today lecture. So tomorrow morning again we will meet for the another session. We'll start the third day by Professor Dilip Pradhan. So he's going to be very interesting ferroelectric materials and their applications. Thank you very much. Thank you, participants, being cum and these
Thank
things.
you again, Professor Swai, for inviting me for giving
Thank you.
the
Thank you
talk.
very much.
It's a
Yes.
great pleasure. Okay.
And I request this all participants. So I will make a multiple choice questions and collect from all these speakers. Then maybe tomorrow 3:30 we'll arrange a means multiple choice questions. So or the end of the day. So it will better. So just for a few questions, and we will evaluate according to it. Thank you very much to the participants as well as Professor Satyajit Sahu. This is the end of the second day of the faculty development program from the nanostructure material, and it is the application. Thank you very much.
Yeah, thank you.
Hello, sir. I am having one doubt, sir.
There is some doubts.
Yes.
Please.
Sir, myself, Abdullah, sir. Actually, I am preparing that biocomposites. So, is there any facility at your lab characterization?
What kind of characterization you would like to do?
I want to find the thermal conductivity of the prepared composites, sir.
See, as such, because I told you these thermoelectric study, these are purely based on theoretical calculation. So I haven't yet done any thermal conductivity measurement experimentally. So at this moment, yeah, in my lab, I don't have any setup. But if you
Sir,
want to
are
study
you
some,
using any rule of mixtures or something like that, or how you people are doing?
sorry, come again. Like, can you repeat?
Sir, are you people using any mathematical models for the calculations?
No, I use density functional theory, which is the widely used model or theory for studying materials theoretically or doing simulation on the material. So along with that, there are few packages which come to study some explicit behavior or explicit parameters of the materials, but mostly it is DFT.
Sir, have you people used any time that rule of mixture something is?
Rule of
concept.
mixture.
Yeah, yes, sir.
Sorry, I haven't used anything like that.
Sir, one more doubt, sir.
Yeah.
Whatever you people are doing critical calibration, can you also use that ANSYS software for doing the same?
ANSI software does not include DFT into it. It does more of it in a classical domain.
Okay, sir.
Right, but when you talk about DFT, it is basically into the quantum domain.
I think, sir, I have to go through your papers to get more understand. I am new for this subject.
Sure. You can go through our paper, and if you have any doubt, you can always reach me using my email
Sir,
ID.
if you don't
So
mind,
I'll
I will send one email, sir. Can you send me your 2-3 papers, sir, so that I can go through that?
Sure, I can do that.
Thank you very much, sir.
Yeah.
Thank you very much, Professor Sahu, once again. And now I'm going to end this today's session. And thank you very much, everybody.